Is it visible to all? Okay. Is it audible for all? Hello. Okay. Today I'll be focusing on the importance of quantum computing in healthcare research. Okay. So, though the theme of the FDP is on AI and machine learning based healthcare research, because quantum computing is a new field which is also contributing and they have a lot of potential in the working on in the healthcare sector. Okay. So the outline of my talk is like this. I'll just give the little outline about how much potential is there for the healthcare market, how much is the next 10 years, what is the business, and then what are the things which in quantum computing can contribute more to healthcare, which other technologies of the computer science are not able to, right? And then I give a little bit of introduction to quantum computing, and okay, that's how I go. Okay. I hope that most of the audience are from computer science field, or maybe some maybe in the medical field. I feel correct. Is it so, Prajwal? Yes, yes. So in that case, basically, let us see that because it is very important for the faculty of quantum for the faculty of computer science. So that's why a little bit of spending time on little bit of what's the quantum computing, what part of the quantum computing is useful for the healthcare. Okay. So see, basically, I just see that the computing is getting redefined almost like every 2, 3 years or 5 years. Earlier, it used to be 10 years the timeline, but today, if you see that every 2 years, a new field is emerging from the computing. So I'll just quickly spend a few slides on that. Okay. So in the early stages of 1980 and all that, when the computer science itself started in 80s and all that, so then people thought that the part of electrical engineering and then computer science engineering aspects, or that means the manufacturing aspect of the computer, and then a little bit of algorithms, these two constitute the computer science. This is in 80s, early 80s. So later in, by the time 2000 and all that, if you see that, computer science is also serving many areas, uh, name it anything, like mechanical engineering, the medical systems, information systems, cognitive, that is brain related things, and biology, material science, name any field which the computer science was accommodating, and it itself is changing itself, its hardware, its algorithms, and all that to accommodate applications in these fields. Okay, so that's how the computer science started emerging multiple directions. Okay, then so similarly, in not only the hardware aspects we have looked into that, and then the requirements of the various fields. We also looked into that for the algorithms, computer science. We looked into various fields, the approaches, how to solve this one. That's how the we have taken a lot of things from mechanical engineering, from annealing and all that, from the metallurgy, then biology side, genetic algorithms, neural networks from the brain research, and all that. Okay. So in a nutshell, if I can put that, the computing is getting redefined very periodically. Starting, I just gave a quick shot for from 1970s onwards. So initially, we were focusing on the computers were focusing on the number crunching. So that's how the mainframes were very powerful than they were the ruling the globe. So which are I just kept it in the top, and then slowly mini computers research started in the 70s, and then slowly mini computers became dominant in by 80s by the time it reached. So that by the time the where the technology started bottom, and then by the time it came to into the usage and all that, I showed it at the top. So mini computers became dominant. Mainframe computers started being replaced by the mini computers. Then PC started from 1980s, and then PCs became very dominant by 1995s and all that. Earlier to that, we don't have PCs, right? Personal computers. Then network computing, the grouping the many number of PCs together with the network, and then we started network computing started, and network computing emerged by the time 2000 field. It was everywhere. We are using all the labs. We started connecting and all that. Okay, and then slowly at the time, cluster computing started. The parallel computing side, the high performance computing or supercomputing, they started earlier. It used to be to make a supercomputer. It used to take 10 to 15 years of time. The Cray and all those companies used to be there, dominant in the world. They used to rule the world, money, right? So then slowly cluster computing field started from 2000 onwards, and that means in a cluster, small cluster, you can make a parallel computer, big parallel computer, right? Then cluster computers are heavily used from 2003-5 time frame and all that. And at the time, distributed computing field started emerging. Distributed computing means connecting the computers remotely, which are there with the network and all that. We started using as a group this distributed computing. So earlier, network computing is in a lab, basically in a LAN and all that we started using. But this here it is, the computers can be in a different geographical location or different states, different on all that. Okay. Then distributed computing becoming dominant in by 2005. 2005 time frame, we started hearing the grid computing. The whole world was working on the grid computing infrastructures everywhere. Every country that became like a prestigious thing, grid computing. So every country has their own grid computing. India has Garuda is the National Grid Computing Initiative. We started in 2005 and we worked till 2015, 10 to 12 time frame. Okay. So then during that time only, we wanted to grid computing. Basically, we were connecting whatever the supercomputers, the parallel computers across the globe with a high speed network. During that time, network speeds are also very low. We don't have the high speed network beyond 1 megabytes per second and all that. Then slowly 1 Gbps network started emerging, and we are able to deliver computing as a service after the networks also grown for a higher Mbps. Okay, so then slowly the cloud computing, because the grid computing we used to put lot of servers onto the net and all that on the clusters on the grids, but let any number of high-end servers we used to keep, the computing power was not sufficient. Okay, people will be telling, because people started working on big science applications from the 2005-10 time frame, because you remember that Large Hadron Collider experiment was conducted in 2012, right? For that Large Hadron Collider experiment to be accommodated, they have made almost 10 years of preparation for. Okay, we were working on the high computing on the grid computing, and they were working on the storage on the grid, the storage grids. Actually they were starting, because the amount of data which it will generate in that big bang, that's sufficient for is a huge data, and we were not having the storage technology during the time frame to accommodate that large storage of what the experimental output is. So this is one of the big science experiments, and then slowly people started using big science experiments. People started using like astrophysics, biomedical side, and all the people. The computers became a integral part of their this one in their research. Okay. So that's how this one, and because we felt that the number of servers which are available on the grid are not sufficient, then we started looking into how to solve this problem, and that's where the virtualization of the servers concepts emerged. Okay, then we started virtualizing the servers. Then we are able to give from one physical computer, we can generate many number of computers. That's how the cloud computing field started emerging from 2010 time frame or 2011-12 time frame. Okay. Then cloud computing became a reality, and then people started using that. Initially, cloud computing has a lot of inhibitions from the people, that whether we can use the cloud, a lot of security issues people used to talk about, because earlier people were used for using infrastructure in their home, right, in their organization. So they used to feel that if the infrastructure is with me, I feel secure. My data will not be stolen by anybody. So then there are a lot of reservations in the cloud computing would be used, especially banks and all the public sector things. Like even the government was having a lot of hesitant that to use the public clouds and all that. So that's where we started slowly working on it. Then the hybrid clouds came and all that. That is the emergence of the cloud computing. So then, because now the computing is available as a service on the net, people started using the computer infrastructure, which is available through the Amazon, and all these people started giving the services. And then the lot of experiments people generated, and then a lot of data. Till 2012 time frame, the whole world data was almost like zero point 0.6 or 0.67 exabytes. The whole world research data for the last 30 to 50 years of data. And then from 2012 timeframe onwards, because of the extensive usage of the computers and data available, data that issue started emerging, and then the data started growing up. That's how the big data field started from 2015 timeframe. And big data became a reality 2017. And then slowly, because people started using sensors, okay, in most of their experiments, they started using sensors, and then they want to put this instrument on online, and then started in all the fields, whether it's a medical or astrophysics or whatever, name any field, they started using sensing, and sensing became one of the this one. Then people, then that's how the IoT field started emerging from 2017. And then IoT became in full-fledged form, and then 2012 timeframe. Then, so the AI, though it was not a new field, but AI was there in 1990s and 80s also. But thing is, AI was could not deliver the expected out services for all the expert systems. What today we are seeing that, basically because all those previous these technologies like networking was not there, computing power of not there, people started not using it for heavy experiments and all that big, okay. So all that, because of this, in this last 20 years or 30 years, then AI started emerging from again 2012 time frame onwards, okay. Then AI once started emerging, then people started seeing that, okay, not only intelligent computing, then how the computers can be given the capability of learning capability. That's how the machine learning became an outcome of the in AI. One of the branches, the machine learning, and AI and machine learning started emerging from 2020 time frame. And today, if you see that, there are a lot of systems are available with AI and machine learning based systems. And then the quantum computing field started becoming dominant. Need not, like, I don't say that quantum computing started in 2025. It was started almost like a 15 years back when I was in IBM. 2000 time frame, we used to do some sort of brainstorming sessions and all that on quantum computing. This was way back 2005. But it was only in the labs. It has not come into the field, and people started not using extensively, and there are no commercial systems available and all that. But 2025 time frame and all that, if you see that, there's a lot of, now all the many private companies and all started investing heavily on the quantum computing. And quantum computing field today, we can see that Google has a roadmap of delivering a 1000 2000 bit quantum computers. Microsoft has a roadmap of delivering 1000 bit quantum computers, and so on and so forth. Today, everybody, even the government, Indian government also, with quantum computing mission, they have almost put 10 to 15,000 of crores for the quantum computing research project. Not only India, everywhere, US, everywhere. People are trying to see that they do the earlier breakdowns, and then get the invention, so that they can rule the market and the world soon. Yeah, that's all. So that's how the quantum computing really now started emerging, and that's why I just focus this talk on quantum computing based healthcare. Okay. So now let us see what is the potential for the healthcare market and using the quantum computing. Okay. So if you see these projections, okay, today in 2026, that US dollar business of almost $6.59 billion of business in the using quantum computing related technologies in the healthcare. And they have projections like it will grow to by 2036 to $18.4 billion US dollars. And they are predicting a growth rate of compound average growth rate of 10 to 82%. So these are the projections are there by for the quantum computing field in medical application, healthcare and all that. Okay, not the all the fields. Okay, it is similarly it is for all the fields. The quantum computing is going to bring a big market for all the people. That's how people started focusing on the quantum computing research and then deliverables and all that. Okay, now let's quickly I'll see that Quantum computing in healthcare market, I just showed that. Then what are the applications? There are many applications in the healthcare, like the drug discovery, so finding the new drugs and all that, and then molecular modeling, genomics and proteomics data analysis, medical imaging and radiomics. And this medical imaging radiomics already we started using that, and other places drug discovery we started using that, because there is a unique thing is there for quantum computing. For certain applications it works extremely well, exponentially well, right? In the classical computing, you cannot do that. Okay, that we'll see if time permits. Okay, then clinical trials and design and healthcare logistics, also quantum computing can heavily contribute. And personalized medicine and treatment, this is one field which is emerging now, personalized medicine and personalized healthcare and all that. People are looking at that. So there also quantum computing can contribute, and bioinformatics and epidemiological modeling. That is epidemics, you know that, like a COVID and all that we are seeing, all the modeling also, quantum computing can help a lot. Okay. Then these are the applications, some of the applications, not all the applications. And who are the end users? End users are pharmaceutical companies, biotech companies, academicians, academic research institutes, healthcare and medical imaging areas like all the MRI and all that organizations, government, public health agencies, technology vendors. All these are all the end users for these deliverables. Okay. So then what is that for these applications and for these end users? What are the quantum computing actual technologies we use, right? So if I just showed that for the above applications and end user, the quantum technologies type, basically we are talking about quantum computing has a four verticals, you can say there. One is quantum architectures, that is all how to make the quantum hardware, basically we talk about. Then quantum communications, another field which is emerging, and quantum security side, cryptography and all those, very dominantly it is contributing. And so the technology is quantum annealing and gate-based quantum processors, that's the hardware aspect, and quantum inspired HPC, that is parallel computing side. Quantum computers are inherently parallel. That's one beautiful thing actually. So now high performance computing is quantum computing it gives much superior outcomes than the normal conventional classical supercomputers. Okay, and then also in the algorithm side, quantum machine learning, quantum AI, and all these things are emerging, right? And what are the service types which we do that, like quantum softwares and algorithms, we'll see that, and cloud-based quantum infrastructure accesses, and custom quantum R&D services, and then quantum consultancy and integration. These are all the fields, type of services delivered, so people can do the business like. Okay, so quantum hardware provisioning and maintenance, and so on and so forth. Okay, these are all the various things which they contribute to the this healthcare field. Okay, so the in the quantum computing in real world use cases, there are many like that. Like for example, some of them biomarker detection. You know that in the drug design and all that, when we do that, when we give a drug, how the drug is working, how the drug is performing, and all that, they use biomarkers. To this one in the medicine and all that, you might have seen that endoscopic and all. Earlier we used to do the only way is to probe through the endoscopic and all that. They use some biomarkers and see that how any inside any problems are there. And also we have seen that the quantum small sensors, basically people in the form of a capsule they can take, and then it gives a total picture of your internal organs and all that. That's also a reality. Okay, then molecular simulations and drug development, and then also they use in the healthcare logistics, like the drugs display, drug delivery, and I mean drugs distribution and all that. There's a logistics basically, right? That also it helps a lot. Okay, these technology currently some of the challenges are, so when we use the quantum computing and the data of the patients and all that, ethical challenge, how to address that. Okay, and today we are talking about AI has a lot of ethical issues. AI can get into your personal thing and all that, can do a lot of lot of damage also, right? So these things have to be addressed. Not only the technological side, engineers and all that they work, but ethical and other things is the policies by governments, and then the law enforcement agencies and all that, they have to look into that, how to enforce these issues, ethical breakdowns and all that. Okay, so these have to be overcome to make the quantum healthcare solutions a reality to achieve full clinical integration and all that, right? So then current research and the research roadmap, you see that below, the quantum computing side, hardware side and all that. Then healthcare technology evolutions also. There's the roadmap basically. And then how to use the quantum machine learning algorithms or quantum AI algorithms, devise new algorithms and all that. And then start attending to the personalized medicine. Try to understand it. Basically, in the research roadmap, basically we have to understand it fully and its requirements and what are the tools can be used for that, and how it is not breaking the ethical problems and ethical issues and all that. Okay, so like that, these are research roadmap which has to be achieved, and then the drug discovery and biomarker detection and so on and so forth. Like there is a huge thing going on basically. So yeah, also we can use that in healthcare. The quantum sensing is extensively used basically to make certain devices and all that. I'll just spend some time on the quantum sensing, why quantum sensing, and why not the classical sensing what we are having works for us. Okay, I'll just spend some time on that, and little bit I'll spend on the quantum computing, what it is and all that, some fundamentals. Okay, and quantum approximate optimization algorithms, these are the things which are also looking at, and quantum neural networks, QNNs, quantum computing methodology to categorize the which quantum algorithms to be identified for the benefit of healthcare, all these things. Okay, and the most mentioned application, the drug development, drug discovery, and then molecular simulations, and so on. So these are the already people started using that in the labs and all that, using this quantum computing and all that. That many systems are available as on today. IBM's machines are there, Microsoft machines are there, Indian machines are there, at CDAC and all other places, and everywhere there are various types of hardware machines. Quantum computers are available today with the different technologies like photonic based, solid state semiconductor technology based, okay, ion trapping methodologies based, and so on so forth. Like okay. So we'll just quickly see if time permits. Okay, what makes a sensor, the quantum sensors superiority? Because so okay, quantum technology has these principles you might be knowing: the superposition, entanglement, and then quantization, coherence. These are the four basic inherent properties of the quantum computing. Superposition, no, you know that. So classical computing and quantum computing, if you see that in classical computing, every bit is independent, right? A zero, each bit can be a zero state or one state. But in quantum computing, it is not so. Every bit is in a superposition of 0 and 1 state. That means it is in the same state of 0 as well as the 1 at the same time. That is what superposition is that. So that is one of the inherent property of the quantum computing qubits. Okay. Then entanglement. If two qubits we entangle that, then these entangled qubits, you take it to any amount of distance, infinite amount of distance in the universe. And if you do some measurement on one qubit to know what its state is, then immediately it reflects on the other qubit. These two qubits are entangled. And Einstein was wonderstruck of how it is possible, because Einstein has a relativity property, E is equal to mc square and all that. So you know that the maximum speed is it can be possible is they traveling the speed of light and all that, right? So beyond that, so in that case there will be inherent delays, right? If you take the distances are very large, the delays will be there. But here in this case, the entangled qubits, immediately if you do some measurement here in one bit, then instantaneously you can find out the what is the state and the other entangled qubit. So, and quantization. Quantization is the type of signals are very weak signals we can measure. So that is one thing which is very dominantly useful for the quantum sensing, and we are able to measure very weak signals. Classical sensors and quantum sensors, there is a difference. Classical sensors, you know that, right? Any of these parameters can convert into electrical signal and then measure it, right? So, but whereas the quantum sensors, the weak signals are such a weak signal that you can see that it is 10 to the power minus 12 angstrom units and all that. Basically, you can measure that much of weak signals. Okay, and that's how we are able to measure the gravitational waves and all that using the quantum sensing measurements. Okay, and then coherence. Coherence is that yeah, space sensitive detection enables nanometer scale. It will be in the coherent state for a short time and all that. Okay, it's not just a better sensing. Quantum sensing, you cannot just like that. It's a different, fundamentally a different type of field itself, which you cannot imagine that classical computing can deliver that. No matter how much time you work on these classical sensors, you will not be able to reach these sensitivities. Okay, the fundamental new physics turned into measuring technologies. We are using that. Okay, so we know that laser-based quantum sensors, okay, lidar and all that today already available using. So the sensitivity is 10 to the power minus 21. Okay, you can measure that. Okay, so whereas the classical sensors, maybe you can order of the few micro or nano signals, nanovolt signals you can measure. But whereas here 10 to the power minus 21 means you can imagine that how small it is. Okay, so and their applications are, you can see gravitational waves we are able to measure using these laser-based quantum sensors, then nano positioning and lithography, all the space inference interferometers, and all these today it's a reality. People started using this. Okay, these sensors. Okay, and in medicine side, MRI quantum spin imaging, basically. Okay, so Fourier image, you can see that here we are able to see measure very sensitive signals. We are able to see that if a cell became a cancerous cell, the changes, okay, in the sense cell signals, what it emanates is very weak signals, basically. Okay, using the quantum phase measurements and all that, we are able to see that if any cell in the body is there, any cancerous cell and all that, we are able to, even if it is a single cell is there, we are able to identify. That is the beauty of that. Whereas in the conventional methods, if it becomes a big okay, mass and all that, then we are able to detect it. So we are early, for cancer and all that, early detection is what it helps them. Okay, even few cells got cancers will be able to detect using these techniques, using the quantum sensors. Okay, then there are various types of sensors actually, NV center based magnetometer sensors and atom interferometers, quantum gravitometers, quantum gyroscopes. Gyroscopes, you know that in the space, and all the spacecrafts and aircrafts and all that use that, right, to know the position and all that. Absolutely. And then the dark matter detectors in the astrophysics and all that, people are using that. And then quantum radar is another field which is emerging, right? Okay, using the quantum sensing applications. Okay, so if you see these unified quantum sensing view, in the various fields people have started using that, but in the medical side, if you see the MRI systems, okay, nuclear spin quantizations, we are using that. And because every cell, okay, electron has a spin, right? We are seeing the quantum computing hardware, spin-based quantum hardware, right? That means we use the electron spin as a quantum bit. Okay, you know that electron is so small and all that. Whereas if you use the conventional way of classical computing to make a bit of a storage, we use almost like magnets and all that, which contains in that small tiny cell almost like a 20 to the power of 12 atoms and all that. But whereas here, one cell, one electron, single electron can be used as a quantum bit. You know that. That's how the densities you can achieve that in the quantum computing. Okay, so the spin of that electron, we can use it for people are using it in MRI systems, the nuclear spin quantizations, and we are using based on that the tissue structures and all that. That's what I talked about recently. I read somewhere people are talking about like that there is some disease. Doctors are telling that the heart some murmurs, right? So there is it's a problem for the people. The heart sometimes generates some weak signals about the heart condition. So they call it as a murmurs. Okay, and to know that you need a very sensitive sensors, and people have to be there inside the their intensive care unit and all that. But whereas the doctor said that if we use this quantum technology, once we know that this is the bit, okay, one quantum bit is being entangled bit, you can put it onto the patient. That no matter the patient, wherever he goes, instantly doctor gets the signal that I don't need to wear a big sensors. Like for this example, in the currently we are using some pacemakers, etc., for knowing the heart conditions and all that. This pacemaker, you know that it's a small device. They'll embed it into the heart, and then you cannot take any electromagnetic signals nearby interference. It interferes and it works. The interference interferes the work of the heart and all that. So whereas these quantum sensors which you put it into the human body, they have no, because they found that these single photon detectors are available today. Where people are working on that, and then we can detect from any long, even one single photon, the changes we can measure it from a distance. Okay, yeah. So sub nanometer resolutions and medical, and then they are using this also in the brain mapping. Brain mapping is a big research. You know, human brain, blue brain project is one of the big science projects currently active today, and people are trying to map the total human brain, find out the functionality of the every part of your brain. Why we are doing that? Basically, we are making the artificial brain, and then the people with Alzheimer's disease and many diseases, their brain gets some part of the brain gets spoiled. So we are using this artificial brain chip and put it embedded into their system so that they will be able to walk. So there are a lot of people like paralysis and all that, people not able to walk, and using these instruments and all that, people are able to run, people are able to see. The blind people are able to see today. Yeah, all these things are the outcomes basically. Okay, and yeah, in these quantum sensors in all these fields, like atomic clocks, people are working laser sensors, quantum standards, and all that. Okay, so basically, it is a sensing the inherent technology, basically quantum magnetism and quantum physics and all that. I will not spend much time on this. Okay, so that's all about the whatever the in healthcare, what are the sensors and all that. Okay, I spend some time on introducing the quantum computing and what are the difference between the classical computing and the quantum computing, and how we can use it. Right. Okay. So in quantum field now, these are the four verticals mainly contributing. Even government of India also has allocated quantum valleys and all that. You know that they have given some organizations to work on this one. Okay, the quantum sensing, quantum hardware development, quantum algorithms development, and quantum communication. In quantum communication also, it is doing wonders. IIT Madras is the center hub, and sensing side somewhere in Pune and all, ISAR Pune and all that. And quantum hardware side, we have seen recently Amravati, there is a quantum valley and all that. People are working on that. And quantum algorithms, all the computer science people, many institutes, many IITs and all the people are working on that. Okay. So the fundamentally, what is that initially changed in this? A little bit of few things I'll spend on. The photoelectric effect was first discovered by Hertz in 1887 during investigation into radar waves. Basically, they started giving a high voltage experiment these are all. Then when the high voltage applied across two electrodes, then it started generating the radio waves, and then you can see an arc, okay, between these two electrodes. This is a spark. And then had found that the arc is in the form of a very beautiful ultraviolet light between these electrodes. Then spark was basically because that means basically it is a ultraviolet light basically. That means that the transmission is very stronger and all. Okay. So then this was in 1857. Just see that 1887 have did these experiments. Then in 19th century, late 19th century, the photocell was detected. Okay, so and they're able to measure the photoelectricity. This is a photo cell, basically what I have shown in the below, right? So on this is a vacuum tube, cathode and when the light falls onto the cathode, then the cathode starts emitting the photons, and these photons get attracted towards the anode, and there will be current in the circuit. Okay, so this is the beginning of when the light is shown on the cathode of photo cell, electrons started releasing, and they're attracted towards this one. Okay, and then that's all. What in the 19th century, the photo electricity. These are the first photo cells, basically. Then in 1905, Albert Einstein started giving the reason why it is so that. Okay, people thought that initially light travels in the waves, right? Photon theory of light earlier. Then, but this experiment they are not able to. Then he explained that the experiment is basically an evidence of the photoelectric effect, and it's not basically because of the classical wave motion of the this one. Light travels as a photon, quanta. A photon is a travels in energy packet. That energy packet is what is named as quanta. That is the beginning of the quantum computing field. Okay. So Einstein proposed that although light exhibits wave-like properties, initially Newton thought that light travels like a straight line. Then later somebody said it travels like a wave, and then Einstein said that no, it will not like this one. It is electromagnetic waves, and is a packet of energy is this one. Okay, so then he named this as a photon as a discrete energy packets called quanta, and the energy of an individual quanta depends on the frequency of the light, which you okay. So okay, this part I'll skip that generative and all that how it is helping. So then the hybrid quantum computing, nowadays we are the systems in the hardware basically we are talking about certain things classical computers can do, and in the quantum computing it is totally different fields, different principles than the classical computing. But for certain parts of the this one we use the classical computing in this. So that's all hybrid quantum classical programs like near time hybrid. So there are two models you have shown here, the near time hybrid programs and then real time hybrid programs. Basically, it talks that so it makes classical decisions based on the controlling part is done by classical computers, and then actual hardware portion is done by the quantum computers. Okay, yeah. And so like it sets the classical computing sets the logic of the parameters and all that for the functioning of the quantum computing, and then after then it is done is after the measurements are done, results are done. Based on the results, again classical computers are used there, and then it will set the parameters, it will change the parameters in one way. Okay, so this is how the hybrid architectures of the classical as well as the this one. Okay. So this computing field, like previously what I talked that computer science is a conglomeration of, it is serving for various fields, like it is basically it is accommodating mathematicians, and we have taken certain principles from there, and then every field, name any field, the computer science it embraces it, and then it uses some things from there. It takes that, like philosophy and all that we have taken from. That's how the AI field emerged from the philosophy field, and mathematician, logic, algorithms, etc. from the mathematics, and like that various in the stock market and all the decision making systems, like that everywhere every we have taken something and we have given to the that field. Okay, so that's now let me spend some time on the quantum computing hardware. Here, I may not, some slides I will skip. I didn't optimize these slides. This one, okay. So basically, we just see that a small history about the quantum, how, what are the basic principles of the quantum computing and all that, and what is a qubit, and what is basic properties like superposition, entanglement, decoherence, and all these things, and how some, for the computer science people, you know that gates and all that, hardware part is we realize based on gates, like all those. Similarly, in quantum gates, what are the quantum gates available, possible, and then how can make certain circuits, and then as a algorithm side, what are the quantum algorithms and all that. I think those are the things I will spend some time. Okay. So then, okay, this is the quantum supremacy, basically a real problem. If you run it on a classical computer and also you run it on the quantum computer and you compare their performance, if the performance which the quantum computer delivered on this application is much superior, then there's a quantum supremacy. It's already proven. People started certain algorithms which are available, which are some applications which are available, which are doing well in the classical computing, and they tried on the quantum computing, and they compared this. This is already, I think, 2021-22 time frame, quantum supremacy are already proven. Okay. So, what are the things physics consists of classical in the quantum computing? From physics, we use the classical mechanics of the from physical field, and we use the theory of electromagnetism and thermodynamics, and yeah, okay. Then dynamics of this one we use Maxwell's electromagnetic magnetism equations and all that. And radiation, we talk about the matter and radiation frameworks from the physics. We use that. And then interactions between matter and radiation using all these, this one, Lorentz force and thermodynamics, they are being used. Like that, various things which are being used. Okay, domains are relative domains, Einstein's theory of relativity and Newtonian mechanics for at high speeds of the light and all that. Okay, and microscopic domains, subatomic particles, the boson cells and all that, the large hadron collider. So you know that there's an interesting experiment which has happened 2012 time frame. There were two theories for the universe creation, right? One is the Big Bang theory, and other one is so that the entire universe is collapsing into the one this one. One field is the entire universe blast got big blast. Then after that, within the few microseconds, milliseconds, the entire universe got created. How it got created? People thought that there are certain particles were emerged. They named it as the God particles, like bosons and all. Okay. So somebody sarcastically, the people, the media people named it when this experiment was going on from 2002 to 2012 time frame at okay, in Germany somewhere. So this is a 25 miles cyclotron below the earth, and the particle will be accelerated to a very high speed, and the whole of the cyclotron is at a supercomputing, that is below Kelvin, minus 273 degrees centigrade, and because when the Big Bang happens, it generates almost like a 2 to 10,000 degrees centigrade of heat, like what's happening in the middle of the sun, right? So they created that environment to contain that. No matter anything you contain that, it will get melted, right? The whole infrastructure get melted. To contain that, they put this cryogenic shielding and all that. Okay, so they did at that time the media people named it. These people are experimenting on the God particles like that. So, but it is really after the experiment 2012 it has happened, and then 147 countries participated in this experiment, and they analyzed that, and yes, they said it is correct. The particles are this one, but they after the Big Bang it came out, and then its lifetime is very small, few nanoseconds, right? And within that time, the whole universe got created. That's what the theory was proven. Okay, then in computing science, you know that Moore's law. That Moore's law, they thought that the chip density is getting doubled every 2 years, so 18 months basically. And today, it's almost like in 2015, 18 time frame, they said Moore's law almost like reached its saturation. But after quantum computing started, yeah, Moore's law is not saturated, still going on. Because now, earlier we are making that to make one quantum gate transistor, we are using almost like thousands of atoms, right? But whereas the quantum computers are made with single atoms, single electrons, right? So that's how the, okay, okay, the classical computing, you know that, and just I'll skip that. Okay, there is certain experiments which on the quantum computers, like small example is a game. Suppose the computer can human people can play this game with the computer. Suppose first initially the coin is shown with the head or this one, then the computer plays, it tosses it, whether it tosses, and then later human tosses, then later computer tosses, and after 3 or 4 rounds, if you can able to predict that, what is the outcome? Is it a head or tail? So in the classical method, if you see that, there is a chances of 50-50, right? 50% probability, which can be head or this one. But using the people quantum computing, so in the conventional sense, these are the probabilities, right? Player probability 50% around that. Computer has a 50% probability. But using the quantum computing, we are able to say 90% we are able to predict the state. Okay, this is very interesting game basically. Okay, okay, that's what basically I want to show that. And quantum computing is based on quantum physics. Quantum physics talks about the behavior of microscopic systems like microscopic atoms, molecules, and fundamental particles like electrons and photons. Okay, classical computer talks about the atoms and the conglomeration of atoms and all that, like a transistor. Transistor is made up of many number of atoms, right? But whereas here, electrons, inside an atom there are many electrons and all that. Okay, small particles. So quantum computers talk about quantum computers operate by controlling the behavior of these three particles, okay, in a different way, okay. So that's how the quantum computers are different from the classical computers. Just like you cannot compare these two actually. Okay, you have a candle is one technology and light bulbs are different technology. No matter any number of candles you put, you cannot make a equivalent bulb, right? Similarly, the quantum computing is not a compare. You cannot compare with the classical computing, but it has its unique power and all that. Okay, it's a quantum computer is a new kind of device based on the science and quantum mechanics. Okay. So, okay, yeah, the same point. A computer that uses voltages following and the circuits, gates, etc. But whereas the quantum computers, we use quantum bits, qubits we call it. They are based on electrons. You can make an electron, a trapped ions, or a photon-based quantum bit and all that. Okay. And quantum computer has unique properties like superposition, entanglement, here I just showed, and coherence and all. These are the inherent properties of the quantum computers and quantum bits. And they are based on the quantum mechanics, which is the of the subatomic particles properties there. Okay. Okay. So in the same game, what I said, when we use that, they experimented on the IBM computer, and 376 students participated in the previous game on the IBM computer, and the player winning rate is only 3%, whereas quantum computer always wins 97%. Any number of games they played, and then statistically they collected this data. Okay. So what makes the quantum computing superior? Okay. Basically, we have to see that, and okay, this I'll skip this. Yeah. So in a regular this one quantum bit, so regular classical computing, the bits are 0 and 1, right? So we use the bit can be 0 or 1. So we can assign one bit to represent the head and tail of that, and it will be in that state only. 0 either if it is 0, 0 state. If you change it, the bit gets modified into one state. But whereas in a quantum bit, qubit we call it, the same bit will be in the superposition state. That means it will be at the same time in 0 state, also in that, 1 state is also in that. So we can say that, so how much probability, so like below if you see that example, qubit have 70% chance of being 0 and 30% chance of being 1. We cannot say absolutely or 100% chance of 1 and 0% chance of 0. So that means it is 1. So like superposition state can always in this state 70%, 30%, 30%, 70%, 1, like that we define that. Okay, this is called superposition. That means every bit is always in both the states, one state or if it is a cube bit. Okay. Okay. So quantum bit, qubit, we call it. The smallest unit of information in a quantum computer is called qubit, similar to our bit in the digital bits in the classical state. So it represents the state of the wave function. Okay, that is a wave function is a Schrodinger's equation. We can say that it is a superposition state actually. So every qubit is represented by a wave function. Okay, so it will be both in one state as well as the one on one. So basically in electrical signals, what we use in the classical computing. Either it is a electrical high pulse is 1, or low pulse is 0, right? But here it is in the both states. Okay, so qubit can be 1 or 0 state. The two states of a qubit are represented by, in a Dirac notation, we say ket. We call ket 0, ket 1, right? This is a Dirac notation. And many ways to implement how do you realize this 0, that means a bit 0 or bit 1. So the bit can be realized using either it can be nucleus spin in an NMR. So that means if it is a spin positive up, the electron spin up, right? Then it is a 0 state. It's a spin down can be 1 state. Or if it is a photon, it is used as a qubit in the hardware, the quantum computing hardware. If you use a photon as a qubit technology, so the photon has a polarization, right? 0 bit is horizontally polarized, and photon has 1 bit is vertically polarized. Like that, you can use that. So the vertical polarization, you can use it as a 1 state for the photon, or horizontal polarization can be used as a 0 state. Okay, or if it is the energy of an atom, there are atoms have the energy state, right? Ground state and then excited state. Like we know that the Bohr's formula was there, the 1s2, 2s2, that orbits, right? So the ground state can be represented by 0 state if it is a atom energy state, and excited state is represented by 1 state. That is basically every atom we can identify the valency band and conducting band. So if the valency band is the ground state, and when you exit an electron, when you exit that atom, it goes into the conducting state, right? So that will be we can take it as a 1 state. Okay, that's what the energy state of an atom. Or polarization pair, like that. The quantum computer hardware qubits can be realized in any of these technologies. Okay. Um, so either you can use semiconductor qubits, or the photon qubit, or spin in the electron qubit, like that. So all its superposition also described in the same state. All these, whatever we discussed as the hardware qubit, for realizing the qubits we use, all are in a wave state. Okay, wave state we represented by this one. So we'll show the each qubit wave state very quickly. So 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 it will be simultaneous at two states, like all these. These are the, so if electron has its own spin, it will be rotating on itself, and also it will be rotating in the orbit, right, in the atoms. So based on that, if it is based on the clockwise rotation, anti-clockwise rotation, that is it forms the magnetic poles, and then use that spin up, spin down, like that's how they name it. Okay. So then the wave function is represented by alpha times of 0 and beta times of this one. I'll just show you that. Okay, there are many potential applications here talked about. I'll skip it for the time being, this slide. Okay. So, yeah. So these are some of the applications basically which I could have shifted into earlier. Okay. So these are some of the applications basically we are talking about in the quantum using the potential applications, quantum cryptography and all today. And there are encryption we are using. The quantum cryptography is one field emerging. So people are looking that once the quantum computers come, no matter whatever the cryptography algorithms you are using, they can be broken. So that's why people started preparing for post-quantum cryptography algorithms. People started because no matter, see, we have the SHAR algorithm and all that with the 256 bits and all that. We are talking about public key and private key and all that, and it's a hard to break it. So okay, we are using that, but that can be easily broken the moment you use the quantum computers. Okay, so and we are in the security. It has a 17 billion, much more market today, right? A lot of security apps and all that. This is the molecular modeling and all that, which is being we talked about already, healthcare and all that, the molecular simulations and all that. and drug discovery and all, we use that. Okay, the molecular simulations and all that being used, find also to find out the disease and all that is previously. Okay, and this is another application like teleportation. Basically, people in the quantum communications, people have started using this. Right? Once two entangled particles you take to any distance in the universe, infinite distance, and if you do some change here in this one bit, the other bit instantaneously changes instantaneously. The moment you do the change here, you can see that. And this they are using it for the quantum communications. This property, teleportation is being extensively used. People are working on the quantum algorithms for communications and all that. Okay, there are many algorithms already in use and all that, teleportation and all that. Okay. Okay, this is a quick, this one is a classical bit and all that I can already talked about. This is below is the quantum computer is a super bit quotient. Every bit is it in a zero state at one state. This is we represent, or it can be in multiple states anywhere, right? Every bit can be in multiple infinite number of q dots. There is another thing is called q dots. Okay, that's also emerging. That means with less number of bits, you can represent a lot of information. You can represent for see, you know that to communicate four states, we need two qubits, two bits. Okay, if the information has 1024 states, then we need 10 bits, right? 2 to the power of 10 is equal to 1024. So like that, the number of bits in a classical computer we decide based on the how much of information we want, the storage and all that. But whereas the classical computing, it is not that way. So even one bit, it not only stores one state, 0 and 1. It can even save multiple states in that one bit information. Infinite number of information can be stored. That's what the q dots and all that is coming. Okay, so that's why you don't need a very big. Say you know that in the earlier classical computers, we measured the power of the computers based on 8-bit computer, 16-bit computer, 32-bit computer, 64-bit computer, and so on. Right? So it is 16-bit computer. The amount of storage we can access is 2 to the power of 16. That's how the computer science evolved, right? And large amount of storage we want, then we need 64-bit computers, 120. But whereas in the quantum computers, it is not the scenario. Okay, so that breaks that classical approach. Okay, and this part I already talked about. So this is how the quantum computing evolution has taken place. I will not. Okay, so the hardware side below is this one, and top is the various algorithms and all that. I'll skip this part. Okay, so yeah, this is the same thing in history and summary of how the quantum computing evolution. Today, 2020, Chinese researchers claimed that they made a 76-bit qubit computer systems available, and by 2020, IBM makes that they will make a quantum computer of 112421 bits, and I think already there is the 1000 bits they already reached, right? And Google has 2000 bit, 2000 or 2000 qubit computer they are trying to make. And like that, there are roadmaps. Every company has their roadmaps in the making the quantum computer. Today, already 37 bit like the computers are available in the country, various research organizations in country. They made based on the photon and all that, whereas Microsoft using the trapped ion based computers, and some people are making semiconductor based qubits and all that. Okay. So the quantum computing industry, if you see that already people started, there are some quantum computers are delivered. So 1999 D-Wave, some few bits, few qubits. In 2007 time frame, I saw D-Wave, some 12-bit computers in some of the supercomputing conference in US and all that. But today they have, I think, more in the D-Wave only, the D-Wave based quantum computer is only, I think, in Amaravati, they also delivered that. And a lot of people are working in the country also. Okay. Various, okay. This is the, I'm skipping this. And okay, this is a picture of the Chinese 76 qubit photon based. This is a photon based qubit quantum computer, and I think IQ NQ maybe of Microsoft. It's a ion trapped computers, and IBM follows the supercomputing, superconducting qubits, right? The cryogenic based qubit quantum computers, and D-Wave also it makes superconducting qubits. Okay, and there, if you see that there are a lot of people in the quantum computing race today. Okay, and almost like today people in the investments, people are doing almost like these are the some figures like in 2024. Today it is much higher there. Okay, all the people are investing in the quantum computing side. Okay, yeah. And European side also, these are the investors in the quantum computing landscape. How much time I have? Based on that, I can spend time. Okay, so let me see if I can do something like yeah. So in the mathematically a zero, the Dirac notation we said uh, one bit is okay. One bit is either it can be 0 or 1. We represent it by a ket 0, ket 1, right? Ket notation. That's the Dirac vector notation. And mathematically, we see that 0 is mathematically it is 1 0, and then 1 means 0 1. Okay, it's a column matrix. Okay, so let us see that some properties and all that. Identity matrix means anything multiplied by the identity matrix itself. So if this is identity matrix, and if you multiply this with the this uh, uh, variables and all that, it will not change, right? So this is the identity matrix. Okay. So I just little bit show in the mathematical and then how the actual gates are realized and all that. Okay. So these are the four operations possible with a single classical bit. Okay, single bit operations. There are one is identity. F of x is equal to x. Is it that means you apply this function f x on the x, it will not change. It will be same. Like means 0 bit will be only 0 state. If you apply this function on the 1 bit, it should be in one state. Okay. Now let us see this this identity this identity matrix is 1 0 this one, and I said the qubit 0 is 1 0, right? In the previous one I talked about, right? This is 0 is equal to 1 0, 1 is equal to uh, 0 1. Okay. So you do this, then you apply this. If you apply this identity function on 0 bit, the result is again 0 bit. Or if you apply this on 1 bit, the result will be 1 bit. Okay. So negation. You know that what is a negation bit? If the signal is high voltage, the negation of that is 0, right? So f of x is equal to minus x. So 0 bit becomes 1 bit, 1 bit becomes 0 bit. So this is the negation matrix, and you apply this function. You apply it on to this. If fx is equal to 0 1 1 0 matrix, you apply it on the 0 bit, it becomes a 1 bit. You apply it on 1 bit, it becomes a 0 bit. You can see that. Okay. Similarly, constant. Whatever you do that, you apply this function onto this, it becomes a constant 0. And similarly, constant 1 function and all that. You can see that. Okay. So then, okay, the gates I will show a little bit. This one. These are some quantum mechanics and classical mechanics comparison. I will skip this part right now. So when we are making the IBM Google, this one superconducting based technologies, right? Cryogenic and all that. So Rigetti, DVU, IBM, Google, all their computers, supercomputing are based on these superconducting loops. Okay. Honeywell, INL, these are the basic qubit hardware is trapped ion technology they use that. Whereas Intel Corporation, HRL, they are using silicon-based, semiconductor-based qubits, okay? Quantum dots, we call it. And Microsoft is topological qubits, okay? The trapped ions technology they use that, okay? So the smallest unit of information is the quantum computer. And okay, this part we have seen already. Superposition will be described by the wave function. I think I'll show that. This is what the wave function is. Okay, alpha times of 0 plus alpha times of 1. So every qubit will be in this state. So the psi is represented as psi is equal to alpha times of 0 and alpha 1 times of 1. This is the wave equation, the conventional wave equation or Maxwell's wave equation. So it is, that means every bit is a superposition state of 0 and 1. When we do the measurement, this bit collapses to one of the state, either 0 state or one of the state. Okay? So and that's what this one. And this is a block sphere representation of the qubits. Okay. For the time being, we'll skip that and we'll spend some time later. Okay, quantum gates is in the classical computing. This is a NOT gate, which I showed that in the right in the quantum computing. This is called poly X gate, right? Poly X gate is what it does the negation. Okay, if the q bit input is 0, it becomes 1. With 1, it is represented 0, and its functionality is given by this matrix. Okay, the poly we have X gate, poly X gate, poly Y gate, poly Z gate. Three gates are available. One is for incorporating the phase difference, and two are from the converting to 0, and one is not no change. So it's equal to not. See, this is what the conventional classical computing. Just I'm trying to tell this so that you'll understand. You know all this classical computing, what we are doing that in quantum computing, how we do that. So it is this. This is a circuit in the classical computing like an AND gate. So the we can make in the quantum computing the circuit will be similar to somewhere like this. Okay. So okay, but the beauty of the quantum computing is the operations are reversible. See, whereas in classical computing the operations are irreversible. Suppose if I give the AND gate output b 0, if it is 1, can I find it out? If I want to reverse this operation, can I be able to find out whether the b1 was 0 before this operation was done, or b2 is both are 1 1, then only it will be 1. Both are either one is 0, output will be 1. So these are all irreversible operations. In classical computing, the operations are irreversible. Another good property of the quantum computing is operations are reversible. I can go back to okay, how I have evolved to this state. So this is one big application in which is being used. We find out evidence, right? Evidence of how you reach this state. So this is one big thing. In classical computing, to do that, we do a lot of struggle for that. Okay, but whereas it is possible with ease, we can do it in the quantum computing. Okay, yeah. So that means suppose I told that when you molecular simulations and all that, you allow the molecular simulation to happen, and then you have reached the final state when you did the measurement. But for that to reach, what is the previous state? If I want to this one, I will be able to find out in the quantum computing what the previous state, previous state, previous state, so that the entire evidence I can reconstruct. But whereas it is not possible in the classical computing to do that. For that, to achieve that, it is a lot of overhead. Okay, I think I'll skip. Okay, yeah, this is another this one. Okay, this is called this spooky. This is all Einstein said. Observing this, how it can be at the same state. So the cat in the room, it can be in both dead state as well as the live state. If you say it is dead, you can make it okay live, or you can, because reversible and all that, right? So that's what okay. Anyway, this is when we have some more time, we spend more time on that, all this problem. Okay. Let me quickly come to a conclusion. There are a lot of questions still there. People are trying to solve that error correction and all that. One of the challenges. Okay. Okay. I think I will stop here.
So, so thank you, sir, for your valuable talk. I feel, is there any question? Otherwise,
Yeah, feel free to ask questions.
yeah.
I'll be glad if you can answer
So, is there any question to sir? So he will answer.
questions.
You can. Okay, they can also put in the chat box so that sir will address the question. So if anyone don't have questions, so I will thank our respected professor. So is there any question still? In chat, check. No question. So okay, thank you very much, sir, for your valuable talk in details. Mostly you have uh, hmm, covered quantum computing, quantum machine, and quantum beat, quantum gates, and as well, yes, some special computing, how this computing now in the present shape. So there are many things you mentioned, and these are very important topic you cover today. So uh, you are very inspiring for us, and you had great for the session. So I'm very much thankful for you for the session. So it is good for us to learn from you, sir. So thank you very much for your uh, incredible and inspiring session, sir. Thank you so much, sir. Time should be up to now 15 minutes. Okay, after 15 minutes we will rejoin.
Jill sir, are you available? Jill sir, are you there? Sir, now now we are going to start the second session uh, of today, and it's over to Dr. Saidez for the introduction of our resource person. Okay, thank you.
Okay, sir. Good afternoon, everyone. Now it's time to move on to the second section of the faculty development program. This section is on the topic from unit to foundation model, evolution of medical image segmentation. It's my pleasure to introduce today's resource person, Dr. Senior Francis, a dedicated academic researcher and innovator in the field of computer science and engineering. Dr. Senior is currently serving as a project manager at CEDAC Trivandrum Health Technology Group. With over a decade of experience in teaching, research, and innovation, previously she served as associate professor at Jyothi Engineering College, Thrissur, where she has been shaping young minds since 2007. Dr. Senior Francis hold a PhD in computer science and engineering from NIT Calicut, where she specialized in AI-driven medical image segmentation for radiotherapy treatment planning. Her dedication towards research, innovation, and academic excellence and mentoring has made her respected academician and researcher. We are delighted to warmly welcome Dr. Seniors to today FDP section. Over to you, ma'am.
Yes, good afternoon. Shall we start now?
Yes,
Share
ma'am.
my screen.
So,
I think my screen is visible now. Is it visible?
Yes, ma'am, it's visible.
Okay. So my topic is actually about medical image segmentation using deep learning techniques. So initially it was using unit, now it is unit to foundation models. So we will just see the path of unit to the foundation models before doing the medical image segmentation. Before moving on to the medical image segmentation, we will just see how the image segmentation happens. Okay. So these are the topics I'm going to cover today. We'll just see what is image segmentation and we'll see some techniques used for medical image segmentation or image segmentation. And then we will see unit architecture And then we will see some variants of unit architecture. Then different case studies using unit architecture, how we will be able to do medical image segmentation, mainly on CT. And then some transformer models, then foundation model architecture. Okay, these are the topics we are going to cover today. So first thing, what is an image? Because we are, is there anyone new to medical image segmentation or new to deep learning? I think all are a bit aware of all these topics. So I think the very minute details no need to explain. Still, we will just see what is an image. An image is a visual representation of a scene or an object, and that is represented as pixels. Each pixels forms a particular image or a shape. Okay, so we can say an image is an array of pixels, and that means an image will have height and width. Then height and width represents the row.
Hello.
Participants, Dr. Senia is facing some technical issues over there. She will be joining very soon.
Sorry, I'm facing some net issues, and here it is raining heavily now. So sometimes I may get disconnected, and within few seconds it will be okay. So please bear with me.
Ma'am, if your speaker is on, kindly please off the speaker because it
Okay.
is echoing sometimes.
Because to know that whether it is connected or not, I am also connected in the mobile also. Like, otherwise, I will not come to know that whether I am connected or not. I'll just check. 1 second. Okay. Is it visible now?
Yes, ma'am.
Yes, ma'am.
Okay. Okay. So I think have missed some slices? Or nothing much. So we can move just like this. Okay, medical image segmentation. Before going on to medical image segmentation, we will see what is image segmentation. In image segmentation, what we are doing is we are segmenting an image into different regions. That means each pixels in an image will be a part of another object. That's what medical. That's what image segmentation. Here in medical in image imaging, we have different functions. First thing is classification, then localization, then object detection, then instant segmentation. These are the different operations that can be performed on an image. So first thing, classification. Classification is nothing but we can identify whether that a particular image, what it represents. That is classification. And localization means if we are able to if we are able to identify the region of a particular object in an image, then that is called localization. Here we can see a cat is localized because we will be able to identify the exact location of the cat. That is called localization of the object. And next comes object detection. In the third image, we can see there are two different objects and we are able to identify both separately. Like there is a blue box that represents dog and a red box that represents cat. That is called different objects can be detected separately. And the last one is the segmentation. In segmentation, exactly we are able to mark the shape of each object separately. That is called image segmentation. So this is the main task we are going to learn today. And if we are doing the same process in medical images, then it is called medical image segmentation. So image segmentation and medical images are not two different tasks. Both are same. Only the difference is the images we are going to use for that are the medical images. Next, we will see what are the importance of medical image segmentation in healthcare. First thing is accurate diagnosis. If we have a CT or MRI or X-ray, if the doctor have to analyze the image. Without a doctor, if we want to analyze an image, we need a segmentation task. In the case of tumor and all, if we are giving an image into a model and if the model is able to exactly identify the location of the tumor, then it will be good and that will help the doctor also. That is the first thing, we'll be able to use image segmentation for accurate diagnosis. It will exactly outline the border and organs. Next is treatment planning. In treatment planning, especially in radiotherapy treatment, if we want to do radiation therapy. So if we want to do radiation uh, for a particular tumor, then we have to identify the exact volume of dose that must be sent through a particular region or particular direction to that particular tumor. So when we send or when we pass a radiation to a tumor region, the organs before that region or in between that region and the source of radiation, that also will get affected by the radiation process. So to reduce that radiation process, the amount of radiation dose must be calculated accurately. So to calculate the actual radius, exact dose, we need to know which are the organs present near the tumor. So to identify the organs, we have to do the organ segmentation. So that is a part of treatment planning. And another thing, we have to exactly get the volume of the tumor. So if we are able to do the segmentation properly in a 3D scan, then easily we'll be able to calculate the volume of our tumor. So these are the different methods we can use in treatment planning for identifying the tumor and helping for treatment planning. Next is disease monitoring. In disease monitoring, if we have a tumor, we have done radiation. After doing the radiation, there will be some changes in our tumor region, and that can be analyzed using the second scan. And in the second scan, again we can do the segmentation, and we can compare the first segmented volume and the second segmented volume, and from that we will be able to identify how much the tumor got reduced and all. And improved surgical precision. Of course, in surgical situation, the segmentation is very important. Especially now, there are many robotic-based segmentations are happening. In that robotic-based segmentation, robotic-based surgeries. In robotic-based surgery, it is must we should have the exact segmentation of the region where we are going to do the surgery. Using that information only, that robot will be controlled. So these are the different, there are many other advantages also for medical image segmentation. Here I have listed only few. So we'll see just some medical images currently available, not all, few medical images, which includes microscopic images, Microscopic images are like pathology and cytology images, which gives like tissue information from the tissue samples. For example, for biopsy and all, when we go for biopsy, what we will get, that is called microscopic images. And mammography, then CT images, then MRI images and fundus images, ultrasound images. These are the different types of medical images currently used in healthcare. We'll see how we have to do this medical image segmentation task. The image segmentation now, image segmentation is doing by the doctor or the radiologist manually. In manual segmentation, the doctor have to sit and do the segmentation process using any software tools. Using any computer software tools, they have to manually do the segmentation. So if we are doing segmentation in a CT volume or in a MRI volume, these are 3D volumes. So in a single volume, we will have around 200 to 300 slices. So they have to do the segmentation in each and every slice separately. It will take a long time, around 2 to 3 hours, for segmenting a single person CT scan. So in that case, if you are able to do the segmentation task using in an automatic manner, for example, as we told, if you are able to do the segmentation with the help of a DL architecture, the architecture will automatically segment the entire 3D volume within few seconds. Then we can save the time. That will reduce the what the task of our doctor, and his working time also get reduced. Nowadays, getting radiology is very difficult because we have very few radiologists currently available. So we can save that time, and by saving the time, we will be able to reduce the cost of the treatment also. So these are the main advantages. I'll just give automatic segmentation advantages. First thing is improved accuracy. Second thing, it is a faster process. And third one is the consistency.
No sound, ma'am.
Sorry, again got disconnected. Okay, so these are the different advantages of automatic segmentation. First thing, accuracy. Second thing, it is fast, and third one, consistency, and it reduces the manual effort, and etc. Which are the different approaches for doing automatic segmentation? Automatic segmentation can be done using digital image processing approaches like thresholding approach, edge-based segmentation, region-based segmentation. These are the different approaches for medical image segmentation. That is a basic digital image processing task. And second thing is the deep learning based approaches. In the deep learning based approaches, we have mainly CNN based architecture. Now, CNN based architecture gives a better segmentation than the artificial neural network based architectures. In CNN based architecture, we will see some deep learning operation that will be used for segmentation. First thing is the CNN stands for convolutional neural network, and convolutional neural network. Okay. In which the first operation is convolution. Second one is activation functions are the pooling operation is the up convolution, normalization, loss function, and optimization. These are the different activities we have to perform in segmentation task. We will see each and every one separately. First thing is convolution. In convolution operation, we have an image and we have a filter. So this filter will be applied onto our image. That is, we are performing a dot product operation, and the sum will be given as the result. So here we could see we have a 3x3 filter, and we will apply the 3x3 filter in the top left corner, and we will do the dot product. So we will get 4. After getting 4, that filter will be moved towards right. Again, the operation will be happening, and finally we will get the result. The result what we get after the convolution operation, it is called feature map. Okay. So when we move one row towards right, then that movement is called, the movement is called stride. Like if we can move one row apart, or if we want to move 2 rows apart, that also is possible. So depending on the stride value, the movement happens. Then we can see a word called padding. Here we can see, here we have the image of size 5x5, and when we apply a filter of size 3x3, the output is having the size 3x3 only. Actually our input image size is 5x5, but we got the output as 3x3. So if we want to get an image of same size, then we have to do a padding operation in our image. So we have to add zeros on top, left and bottom regions, so that we will be able to get the actual size output while applying the filters. Then represents the receptive field. When we apply a 3x3 filter, this region, the filter could see only the 3x3 region. That means that 9 pixels only at a time. That is called the receptive field. And when we move to the right, then it can see the next 9 values like that. So this represents, each filter will be able to see 9 pixels at a time. This 9 pixels represents a receptive field. Here we can use dilated convolution. In dilated convolution, instead of going to nearby 3 pixels, we can take the first row, then the third row, then fifth row. So we're using the same 3x3 filter. So at that time, our receptive field also increased from 3 to 5. So this is called convolution operation. Here you can see in detail, here we have a color image. Color image, as I told, we will have 3 channels that represent, these are the 3 channel values. And here we have a filter. Each filter are 3 into 3x3. When we apply this 3x3 filter on our color image, we will get the feature map. Here we can see the feature map. Here in this example, we have applied 2 filters. W0 is the first filter and W1 is the second filter. Then we got 2 feature maps, that is the first one, and second one is the second one. So when we use a number of filters, we will get different features of our image. That is what the feature learning happens in convolutional neural network. Here you can see an equation that represents that represents the relation between the input and output number of bits. For example, if we have 5 input, that means n in represents the 5x5, and p represents the padding, k represents the kernel size, that is 3, and s represents stride. So when we apply this, we will get the output, how many number of pixels will be there in the feature map, or how many rows will be there in the feature map. So using this equation, we will be able to calculate how many padding we have to apply, how many stride we have to use, like that. And these are the activation functions as we have used in normal ANN. We already, you may know, like there are different activation functions. These activation functions are used for bringing non-linearity into our convolution operation. So there are different activation functions, in which ReLU is the mostly used activation function because it is a simple architecture, or it has a simple function. So computation task is very easy, and also it gives good results. And next is the pooling operation. In pooling operation, what it does is it extracts the important features from our feature map. So by the time when we apply pooling, automatically the size of the feature map also get reduced. Here we can see we are using a pooling of 2 by 2 filters. That means here we have, this is our feature map. In this feature map, we are applying pooling. So nearby 4 pixels, in from these 4 pixels, here we are using max pooling. So the maximum value, that is 6, will be taken, and from the next column 8 will be taken, and from the next 4 and next 7. So we get a pooled feature map, and this pooled feature map represents the high values in our original feature map. That means the image feature information feature information size can be reduced by taking only the important features. And pooling can be done in different ways. One thing is max pooling, another thing is average pooling, and also we will be able to use filters for pooling. Next comes the up convolution. Up convolution is nothing but the just reverse operation of our convolution operation. And also, while in pooling, what we are trying to do is we are trying to downsample the image, but in up convolution, we are trying to upsample the image. So that's why the image size will be increased when we apply up convolution. Here we have a filter. We will apply that filter on our image. Then using that filter, we will be able to reconstruct the higher image. There are different approaches, in which the first thing is the nearest neighbor approach. In this nearest neighbor approach, there is no filters. What it does is it just fill the nearby cells with the same value. For example, here this is our original image 1, 2, 3, 4. Here this is the upsampled image. So what we does is this 1 will be filled here, and 2 will be filled in the neighbor of 2, and 3 and 4. So we got the double size image from this. And next, another approach is the bed of nails approach, in which the extra rows will be filled with zeros. But the actual deconvolution or convolution, what we use is transpose convolution, or we can also use deconvolution approaches. In transpose convolution, we use a filter for doing this upsampling task. This is just the reverse of our downsampling task. So when we apply a filter on our small image, this is our small image, that means 2144. This is our downsampled image. This we are trying to upsample to its original size. So when we try to upsample to the original size, we can use this filter and we can do the operation so that we will get the exact image size, like exact image values here. That is just opposite of our convolution. We will not lose any information. In the case of downsampling by pooling, what happens is we are taking only the high values. So the low values information will be lost. But when we use deconvolution approaches like this, then those values can be reconstructed using learned filters. Okay. Next is the loss functions, what we are going to use for medical image segmentation. Not only medical image segmentation, for all type of image segmentation, we can use binary cross entropy, categorical cross entropy. These are the one common segmentation losses what we are using. In this, what happens, this is actually these type of losses we will use for classification task. We can say segmentation is a classification task, because what happens in segmentation, it will take one by one pixel and it will classify the pixel into a particular class. For example, if you want to segment a tumor, then the tumor, for example, the tumor will become class 1 and the background will become class 0. So in classification, each pixel will be taken and that will be classified to class 1 or class 0. If it is a tumor pixel, then it will be moved to class 1. So we can use categorical cross entropies are used if we have more than one class at a time. If we have only 2 classes, then we can go for binary cross entropy. And the important loss functions for to use are IOU and dice loss. Dice loss is the most commonly used image segmentation loss function. Here it is an overlap based loss function. Here we can see this blue part represents our predicted output and the pink part represents the ground truth. So after getting the predicted, what we are doing is we are doing an intersection operation. And if both are intersecting fully, that means our output is exactly correct and we will get a die score of 1. Otherwise, we will get a value between 0 and 1. So if the value moves towards 1, that represents our prediction and ground truth matches maximum. IOU is also similar like loss only. Here we can see the function like 1 minus P represents the prediction and G represents the ground truth. It also finds the intersection divided by P union G as shown in the figure. And these are some optimization functions used for segmentation. Most probably commonly used optimization function is Adam. All these optimization functions are based on stochastic gradient descent, and on that we have applied different momentums and different features. Then each optimization will be working differently. So the bus performance optimization function is Adam. I'm not going in detail. So next we will move on to deep learning medical image segmentation of different architectures. First one, we will see that fully convolutional network. This is the full. Before moving on to fully convolutional network, we will just see what is an ANN based approach. ANN based approach means there is no convolution operation at all. So we will have an image. For example, this is our image. First of all, we have to flatten the image. So when we flatten the image, here we have 9 values. The 9 values are represented in a single row. So when we make it like this, immediately the spatial information lost. For example, in the case of an image, nearby pixels are related. So there is a spatial relation between each pixel. That information will be lost when we do a flattening function. And after getting the flattened value, then we will do some linear operations and finally we will get the linear values, and the final linear values will be again split as a matrix, then we'll get the mask. But the thing is, when we apply a ANN approach for convolution, the result will not be that good. Next is the convolution, fully convolutional model. This is the basic fully convolutional model. Here, instead of linear connections, we are using all convolution operations. This is the input. We will do convolution. After convolution, we will be applying activation functions and batch normalization. Then polling operation, again convolution, again polling. And after reaching a particular number of layers, we will do the reverse process. That means upsampling, convolution, and so on. Finally, we will get the segmentation. So here we can see this is a encoder-decoder architecture. Here in encoder, what it does is it will learn the features of the original image, and in the decoding part, the learned features will be converted into the mask, so that we will get a mask. The mask will have values. For example, if it is a binary segmentation, then the mask will have value zeros and ones. 1 represents the actual region and 0 represents the background. And this is another network that is called unit architecture. This is the gold standard of segmentation, medical image segmentation especially. Here, as we have seen before, The architecture is same. It is also like an encoder decoder based architecture. But the important thing is here we can see a line like this. This is called skip connection. This will give the global information of this encoder value to this particular decoder value. We will see in detail in next slides. We will see in detail about UNet architecture. In UNet is the convolutional network architecture for medical image segmentation, and it is developed in 2015 by Ronnie Burcher, especially for medical images. In UNet architecture, its shape is in like a U. That's why the name UNet came. We will see this is our UNet architecture. Here the left part is called the encoder and the right part is called the decoder. And the ground, this thing is last row represents the bottleneck. Here we can see we have an image of 572 into 572. Then these blue arrows represents convolution operation. So when we will apply convolution operation and also plus activation, relay activation. And here we are applying 64 filters. That's why we will get a features map of 64 channels. Again, 2 times we are doing convolution. After doing the convolution, we are doing a max pooling. Since max pooling we are doing 2 by 2, so the image size will be reduced by half. So here the image size is 568 into 568. That is reduced by half, 284 into 284. This is the first layer. Like this, we have 4 layers, 1, 2, 3, and 4 layer. That and these 4 layers are called our encoder. In each layer, the image size will be reduced by half, and the number of filters are increased or doubled. So when we come down, the feature map size will be reduced, but we will have more features learned from the image. And in the bottleneck, it's in detail. The same thing is explained again. This is the contracting part or our encoding part. Here, as I told, we have 2 convolution and 1 max pooling in a single layer. And next is the bottleneck. In bottleneck, it just does the convolution operation. 2 convolution with the 1024 filters. And after the bottleneck layer, again the deconvolution starts. That is called our decoding layer. So this is our decoding. In decoding layer, you can see this green represents the up convolution. So the image size will be doubled again. But the number of filters will be reduced because the number of here it is 1024 filters we have applied. But in green arrow, we are applying only 512 filters. So the output will be 512. And with this 512 feature maps, we are concatenating the decoder layer feature map also. So together here we have a decoder output. This is 512. This 512 feature map will be concatenated with our upsampled value, and again we will do the convolution. So the process repeats. Then one more convolution, again upsampling, and it repeats. So by doing this skip connection, actual information is available in this encoder. Before downsampling, what was the value? That value is present in this. That is concatenated with. So global information can be captured from this particular encoder. And here from this encoder values, you can capture the global information and so on. Finally, we will get the feature map. Here we can see we are getting 2 feature map. One represents the background and the other represents our foreground. So this is our UNet architecture. This is in detail. So UNet combines the location information from the downsampling path with the contextual information in the upsampling path to finally obtain the general information which is necessary to predict a good segmentation mask. Here the main advantage of this is here we are using fully convolutional layers. So if the image size, whatever may be the image size, we can use the same architecture because the number of weights does not change because we are using convolution operation. If you are going for a ANN architecture, what happens is depending on the number of input, the number of weight also varies. So we have to be strictly fixed on a particular size of the input image. Here it is not compulsory that we can use any image size to the particular model because the kernel is always fixed. Okay. These are some variants of unit architecture. First one is the VNet architecture. Initially in 2015, the unit architecture was 2D. That means we are doing the convolution operation in 2D images. After that, in 2016, unit only we have 3D unit. Similarly, VNet is also a 3D architecture. So instead of con 2D, here there it was convolution 2D. Here it is con 3D functions are happening. And there are some difference how they are concatenating and how many convolutions they are applying. Depending on that, we will be able to develop different architectures. So VNet is another architecture like that. And this is another variant of unit. It is called unit plus plus. In unit plus plus, it is a nested unit architecture. Here we can see this is one unit, the outer part. This is an encoder and this is a decoder. So that is a unit. And here we can see here there is a encoder and here is a decoder. Similarly, one here, one here. So we can say here we have 4 units in a nested fashion, and we are taking the output like averaging all the decoder outputs together, and finally we will get the output. So here we can see the one advantage, like the encoder is same for all the different units. Only the decoder part is different. And finally we will, and here you can see multiple arrows. This represents the dense architecture. That means just from the end first here in our unit, normal unit architecture, we can see that encoder information from this layer moves only to the top decoding layer, and here from the second to the second top decoding layer. But in dense architecture, it is not like that. The data moves to all other decoding layers. Here the computation cost is very high, but the output will be more better than the normal unit. And we'll be able to extract small images also, like small volumes in a huge 3D volume. And now what we'll see, how we'll be able to improve the unit models we have designed. What are the different techniques that can be used to improve our model? First thing is the data augmentation. As all know, if we have to get better result, we have to include more images. Sometimes including more images is not possible because the availability is very less. By the time we will go for data augmentation, we will just rotate, flip, or crop, or we'll do some operation, or we'll add some noise to our image, and we'll increase the number of volume of our input data. That is called data augmentation. Second thing is the transfer learning. Transfer learning, because medical images are very less, but we'll be able to get normal images, we'll be able to get large volume. So we will train the model using normal images, and those weights will be loaded to our model, and using that weights we will fine tune with the medical images. That is called transfer learning. But whatever may be the image, like there are some common features like shapes, like circle shape, lines, boundaries, those things are common in every image. So those learning can be extracted from the normal images. So those features no need to learn again. So transfer learning can be used to improve our medical fine-tuning, medical image fine-tuning. Next is regularization. This is used for when we have a problem like overfitting and all. At that time, we will use regularization. There are different approaches for regularization. Next is optimizer tuning. That is also, we can tune different types of, we can try different types of optimizers that can improve our model. And hyperparameter tuning, like we can change the batch size, learning rate, and we can change the architecture depth. So that, and finally the self-propagation, that we will see in coming series. And another approach is the attention mechanism. In attention mechanism, here we can see here I have just given 3 different attention mechanisms. First one is the skews and excitation block. Here we can see we have a feature map. This is a feature map. In this feature map, we have an image. Let's see, okay. Okay. We will have a feature map. Its size is height, width into CC represents the channels. SC is a channel-based attention mechanism. So here, each image, here we can, for example, there if C is equal to 10, that means we have 10 channels. That means in an image we have applied 10 filters. So we will get 10 images as our feature map. In this, each image will be, we will find the average of each image. So we will get a vector like this. Since we have 10 channels, we will have 10, for example, if C is 10, we will get 10 different values. Each value represents that particular image, okay, or that particular channel. Then we will do some computation operations for some linear operations. Here we will do using filter only. By the time the model will learn which channels are more important. Based on that, these values will vary. Some values will become small, some values will become large. That means important images or important portion of the image which is coming to our segmentation part, that will have the high values. So these values will be further multiplied with our original features. So what happens? The important channels will have highlighted and the less important values will have low values. So our output will be something like this. This will give a chance to segmenting important part highlighted. So we will get important parts more impressive. So we will get the output more accurate. That is the one approach. This is a channel-based skews and excitation model. And next one is attention gate. In attention gate, normally we will apply in between the concatenation part. There we have a part coming, from our decoder, that is called X, and also we have a part that is coming from the decoder, that is called G. Here we will do some operations and we will find a single W by H into W values. And in these values will identify which region of our image is more important. And this value will be multiplied with our original output. So as shown here, the high values, for example, here blue represents low regions and this red represents high region. That means important parts are highlighted or important regions are highlighted using attention gate mechanism. And here we have used channel wise, and here we can use it is spatial wise attention. And in CBAM, convolution block attention model, here we are using channel and spatial together. Okay, so that also.
Hello, senior madam. Are you there?
Maybe she is disconnected.
Okay, I think some network issues there, sir. She will join.
Yes, yes.
അയ്യോ ഓക്കെ കുറച്ചും കൂടി ഇങ്ങോട്ട് പോകുന്നിട്ട് അപ്പോൾ പറയണ്ടേ സോറി yeah, yes. Sorry, I did not know that I got disconnected. Sorry. So I think we got disconnected from here, I think. So we'll continue again. Yeah. These are the next we'll see some case studies. First thing is the two-stage unit architecture for doing the segmentation of different organs in thorax region, that is chest region. We are segmenting heart, lungs, esophagus, and spinal cord. Here we are using a two-stage architecture. So here we have a localization network. The localization network is also a unit architecture, and we have a segmentation, two segmentation network. First, in localization network, we will give the input. After preprocessing, we will give the input to the localization network. The localization network will identify the region boundary of each and every organs we are going to segment. So this will give the crop values for the corresponding regions of heart, lungs, and esophagus and spinal cord. Using that cropping value, we will crop the image and we will take the input as separate crops. And these each different cropped regions will be given to the segmentation network. the segmentation network will do the segmentation only on the cropped regions. After getting the segmentation result from each cropped regions, we will combine all together using a post-processing step, and we'll get the final artifact output. Okay, here we have the input as a DICOM image. We have to convert the DICOM image into a NumPy format. That will be done in the pre-processing step. Then we are giving to the model as the input. So here we are using two different unit architecture. For large volumes, we are using a unit architecture, and slightly varied architecture is used for small organ segmentation. See, this is the large organ segmentation. Here we are using unit architecture used for large organ segmentation. This is the attention gate mechanism. As I told before, here we are using that. One input is from that encoder part, the other input from the decoder part. This is another architecture. This is the small used for small organs. Here we can see this is called the dense connection. We are taking the output of multiple encoders to the down encoding part, decoding part. Okay, and this is the results. Results we are not going into detail. Here we can see, like, it takes just 8 seconds for segmenting the entire 3D volume, CT volume. Here we have a comparison. Here only for one particular architecture it takes 6 seconds. The others it takes more than that. So if a doctor is going to do this, he may take 1 or 2 to 3 hours for doing this. And we have tested the data with the data from the hospital, the model with the data from the hospital, and this is the result. So from this we will be able to identify our model is comparatively like generalized, like the model is trained on public data, and this is the result. When we tested the same model with a private data collected from a hospital, this is the result shown. So it is comparatively good. And this is the image. This is the 3D image reconstructed. Now, second case study, we are using Chabot's net architecture. In this architecture, we are using cell supervision because we have a lot of images, CT volumes, but in which a few CT volumes have labeled mask. The other volumes doesn't have the mask. So what we thought is we will use those images also to improve our model performance. So we have done cell supervision with a huge volume of images which doesn't have the mask details. So in cell supervision, what we have done is we have done image in painting, image out painting, and image shuffling. All those techniques we have applied. For example, if we have an image, from that image, some patches will be removed by us, and the model will try to reconstruct that regions. That is one task we have trained for this. Like that, we have trained for multiple tasks. By the way, by doing that, our encoder will learn a lot of things, and those information or those encoder values will be passed to our actual unit segmentation network. So our encoder is already trained or pre-trained, or we can see it is kind of transfer learning, and that is used here for the segmentation. And here exact the segmentation is performed using the medical imaging. Okay, and this is the final result. This we have done for head and neck CT images. Okay, next we will see the case study of a GAN architecture. In GAN architecture, we can see there are two different architectures, like a generator network and a discriminator network. In the generator network is a unit architecture. Here we are giving the image 3D volume as input, and it predicts the mask. Similarly, we have the original mask. This is called the original mask. In the discriminator network, we are giving two types of input. One is the predicted image, predicted mask multiplied with the original image. That is the first input. And the second input is the original mask multiplied with the image. This both will be given as input to the discriminator. Discriminator will get two outputs, and discriminator will find the difference between these two outputs, and the discriminator always tries to discriminate this. So it will find the loss, and the loss, it will try to reduce the loss between this. That means the difference between these two. For that purpose, the discriminator will be trained. Similarly, it will take the generator loss. The generator will always try to improve its segmentation so that the discriminator should not be able to discriminate the original mask and the predicted mask. So in the generator, we are applying two different masks or loss functions. First thing is the generator loss, and second thing is the dice loss. That is the direct difference between the predicted mask and the original mask. Those two loss will be added here, and that will be given to our generated model to improve our backpropagation task, and we will get the improved predictions. This is a GAN architecture. It is called a conditional GAN architecture used for medical image segmentation, and this is the results. This we have used for abdomen CT images. Here we can see liver, kidney, and all. Okay. Next, we move on to VIT, that means vision transformer. In CNN, we have limited receptive field. I already told what is receptive field. In receptive field, if the filter size is 3 by 3, only 9 pixels can be seen at a time. That is the main problem with CNN. The entire image cannot be seen by a CNN operation. So after seeing this small regions, then see local neighborhoods first, and only build global context through many stack layers. The multiples from the multiple stack layers only it will be able to get the global information. But in VIT, here we are using self-attention mechanism. In this self-attention, actually in VIT, what it does is, I will show that in detail. Here, for example, this is our image. The image will be patches. It will be converted to patches. So these are the different patches of our image, and this each patch will be converted to an embedding. Okay, and also we are adding the position of each patch. See here we can see 1, 2, 3, 4. That represents the position embedding of our different patches. Then this data will be given to our attention mechanism. In this attention mechanism, it will identify the relation between each patch with all other patches. So those information will be there for by the we will be able to find using the attention mechanism in the transformer model. So in a transformer model, we will have multiple attention heads will be there. Each attention head will be able to identify the different relations between the patches, and this will be going to the next layer. So this is the basic idea about VIT. Not going to explain in detail now. Here, as in language models, we have query key values. The same thing works here also. Query and key values will be learned by the model when we train the model. Okay, and this is an example. Unit R. Unit R is a commonly used transformer-based segmentation architecture. Here in Unit R, it is having this is the Unit R architecture. Here we have a encoder is given by the transformer architecture, and the output of the encoder, VIT, the output of the VIT is given to a unit-based decoder architecture, and it generates the output. So this is the detail. See here, here, this is our encoder. In encoder, we have a VIT, that means vision transformer. We have multi-head attention. Here we have 12 attention heads, and also like this, we have 12 transformer blocks. And here we have 12 transformer blocks, and it is taking, the decoder is taking input from Z3 represents the third transformer block, Z6 represents the sixth transformer block, and 9 represents the ninth transformer block, and 12 represents the 12th transformer block. Those information is considered as the encoder output, and this encoder output will be passed to our unit-based decoder. And the decoder will do the decoding task, and finally we will get the output. Here the advantage is the multi-head attention will give the global information of our data or image, and better features we will be able to learn. This is the Unit R architecture for medical image segmentation. Here we are using vision transformer as our encoder. And another architecture is the swing unit. In swing unit, the entire convolution block is replaced by transformer. There is no decoder also. Like in decoder also, we are using transformers. Okay, and these are the challenges of using VIT. First thing, it requires large training data set to outperform CNN. We need a huge data for getting a better result. And another thing is computational cost. If we want to train a transformer model, we need large GPU because we have to do a lot of calculations and multiplications using matrices, huge size matrices. So because we have multiple attention head in each transformer block, and we will have multiple transformer blocks in a single network, so the computational cost will be large. Now, another thing is positional encoding are typically fixed at training. For example, as I told, in UNet, we can use any size image as input. Even if we have trained a model with the 512 into 512, but we can, while finding the inference, we can use an image of size 256 into 256 also. And also we can use an image of size 1024 into 1024, or any size of image can be given to our model as input, because the weight value doesn't change, because weights represents the filter size. Filter size, there is no change there. But in the case of transformers, here we have a positional encoding. Positional encoding, as I shown, see here we can see 1, 2, 3, 4, 5, 6. Here in this image we have 9, 0 to 9 positions are there. That means our image is divided into 9 different patches. Okay, that means this model is always, if we are giving an input to this model can handle only 9 patches at a time, and each patch will have a equal size. So we will not be able to find inference of an image which is having a huger size or lesser size. So by the time what we does is, we will just resample the image and we will convert the image into the exact size what transformer needs. We will convert the image into that particular resolution, then we will give it as input to the model. That is possible, but in the case of UNet, that doesn't require that. We can directly give the image as input. This is thing, positional encoding. Typically it is fixed. And next thing is the spatial precision. Yeah, it is very difficult to get the fine boundaries compared to CNN. CNN will be able to identify fine boundaries in segmentation, but transformer can't do that much fine boundary identification.
Senior madam, are you there?
Sorry again. 2 more slides. No, 2 to 3 more.
Okay. Continue.
So these are some common DL challenges. Okay. Next, we move on to foundation models. Why we are moving on to foundation models? Just because the availability of medical images, labeled medical images. We will have a lot of images publicly available, but they are not. It is not labeled. So because of the availability of large medical images, we can go for a foundation model, and using this foundation model architecture or pre-trained models, we can fine-tune our actual model using the label data, a minimum amount of label data. That is the advantage of large-scale models. So that is called a foundation model. So in large-scale models, the models are trained or pre-trained using a huge amount of unlabeled data, and it is doing some self-supervision tasks. So the model will be able to identify the features of the image, and those features can be used for fine-tuning any other task. So for fine-tuning for a particular task, we doesn't need a huge amount of label data. That is the advantage of foundation models. The main three characteristics, it's a scale because we are using a huge million images for training. Second thing is it is promptable. We can use prompt for doing our task. For example, in the case of segmentation, using prompting, we'll be able to do the segmentation. Prompting is nothing but we can, if we are giving an image as input, and we can say we have to do the segmentation in this particular part, that we can express. That is called prompting. Prompting can be done in different ways. We can do a click or box, or even we can give text message, like we can say like please segment the tumor region. If we give a text like that, automatically the segment region will be segmented like that. And transferable. It's transferable means we will be able to do the segmentation even for zero shot. For example, the model will be trained for a huge volume of images, and if a particular image it haven't even seen that particular image, still the model will be able to do the segmentation for a new image. Even that image doesn't seen by the model. That type of images also can be segmented using our foundation models. Yeah. The main example of foundation model is segment anything model, that is called SAM. It is developed by Meta AI, and here we can use different prompts, what is called point prompt, bounding box we can give, mask we can give as input. And this model is trained using 11 million images with the 1 billion masks. Each image can have multiple masks. That's why the number of masks will be 1 billion. Total images are 11 million. These all are common images, not normal images, not medical images. Okay. And the strong performance on natural images and adaptable to medical images, because all the images have so many common features. That's why we can use this SAM for our medical image segmentation also. And this is interactive segmentation. So we can, for creating annotation tools and all, we can use SAM. And after SAM, the next version of SAM came, that is called Segment Anything Model 2. In SAM, it was able to segment only 2D images. But in case of SAM 2, it is able to segment 3D images and also even videos. The model will be able to segment videos. For example, if we can select the image or 3D volume, and we have to select, or we have to prompt only for a first or middle segment, and we can tell them to segment it. Automatically, the model will be able to segment from the beginning till the end. The entire model data will be able to segment by the SAM2 model. That is 3D or video can be segmented using SAM2. After that, SAM3 also came. In SAM3, actually, our detection and segmentation, and also we are able to segment using text prompt. For example, if we have an image, if we or a natural image, if we tell like segment leaves. Also, if there are any leaves are present in that image, all the leaves will be segmented. Or if we can say like segment people, so all people will be segmented. Even we can say only woman, so it will segment only woman. So based on our text input, the model will be able to do the segmentation. It came only in November 19. Next, we'll see a simple architecture of SAM. This is how SAM is doing the segmentation. We have image. This image is given to a image encoder. This image encoder is a vision transformer, and it will convert the image into image embeddings. Okay, the output of this image encoder is called image embeddings. And also we have prompts. Prompts will be like points, box, or text. This also will be converted to prompt decoder. And these two inputs will be given to a lightweight mask decoder. Then the mask decoder will do the decoding task. And finally, we will get the segmentation. The segmentation, we will get multiple segmentation, we will get with the different confidence score. For example, the high confidence score can be the one what we expect. So we choose the high confidence score as our segmented output. This is the SAM architecture. Okay. So these are the foundation models. After that is the common image, normal images. We can, after SAM, this foundation models for medical images also came. Because in SAM, it is difficult to segment low contrast organs and tiny lesions, 3D volumetric consistency. These issues were there with SAM. So for medical images, so many have done reworked on SAM and generated different another architectures called MedSAM, SAM 2D, medical SAM adapter, like that. These all models are fine-tuned using medical images. MedSAM, fine-tuned on 1.5 million medical images, image and mask pairs across 10 modalities. Modalities means the images can be like CT, MRI, X-ray, fundus, whatever it may be. Like this, these are the different medical image foundation models. Okay. Now we'll see some frameworks used for segmentation. Commonly, we will do the segmentation task using TensorFlow, PyTorch, and OpenCV, and also Monai. Monai is a good framework. It provides many different architectures for doing the medical image segmentation. So many segmentation architectures are already available in Monai. We can just download the architectures and directly we can do the training if we have the data ready. And it also gives some loss functions and evaluation metrics. All the libraries are available with Monai that can be reused. That is a good framework for image segmentation. So these are some tools that can be used for annotating our images. One thing is CVAT. CVAT can be used to annotate our medical image if we want to do the segmentation training, and if we doesn't have the manual segmentation, we can create the manual segmentation using these tools. Okay, that's it. Thank you. If you have any doubts, you can ask. I think we are running out of time. No, 3:55 only. Yes, you have any doubts?
Thank you, ma'am, for the insightful section. Participants are requested to post their queries in the chat box, or you can ask directly.
And once again, I want to tell sorry for the inconvenience happened from my side, like disconnecting, connecting again.
It's okay, ma'am.
Okay. I think no doubts. Okay, then thank you.
Thank you so much.
Thank you.
One question in chat box.
Okay.
Can we
Can you
use
just read
SAM
that?
architecture in autism detection?
Autism detection from, it is finding from some image. What is the input to the autism detection? If the input is an image, and from the image that can be viewed by a human, then of course we can use SAM. But I don't think so that from some image that can be detected. I'm not sure about that, like whether images will be used for that and what kind of images we have to use for that. If it is a image like CT and any photo like then we will be able to use it. If it is like a signal or something, then it will be difficult. Anything else?
I think no more questions.
Okay, then. Thank you. Thank you all.
On behalf of the organizing team, I extended our heartfelt gratitude to Dr. Senia for sharing her valuable insight on such an important topic. We also thank all the participants for your active involvement. Kindly fill the feedback form shared in the chat. Thank you all. Have a great day.
Now over to Ujjwal sir for the next session. Ujjwal sir, are you there?
Yes, yes, sir.
Okay, right, sir.
Okay. On. Hello. Hello. Hello, Sandeep sir. Are you there? Dr. Sandeep. Hello. Yeah. So, am I audible, Biru sir?
Yes, sir. Audible, sir. Sir, you are audible. Very nice, sir.
So, I'm requesting to Dr. Sandeep sir, please provide him the sharing option, the PPT sharing option for Prof. Anil Biru sir, please. Okay, sir, now you have shared your PPT. It is fine, no, sir?
Yeah. Yes, sir.
So, before standing this session as from 4 to 5, I will thank Dr. Anil Kumar Biru, Associate Professor, Department of Mechanical Engineering at NIT Manipur. I'm very much thankful for him. He still he managed time because he is busy related to these interviews, other things, some internal assessment at NIT Manipur. So I'm very much thankful for him. So Dr. Anil Kumar Biru, Associate Professor and former Head of the Department of Mechanical Engineering at NIT Manipur, his research area of interest in biomedical engineering, adaptive manufacturing, industrial engineering and management, welding and casting, composite material, and die casting. In 2013, he graduated with a PhD from the Indian Institute of Technology in Roorkee, India. He has been teaching and conducting research for almost 15 years. More than 60 research papers have been published in peer-reviewed journals and 45 international and national conferences, has accommodated more than 1249. So citation with a high index of 14. So under his supervision, 10 PhD candidates have been awarded and 5 PhD scholars undergoing. So in his credit total 12 patent, among them 6 patent granted, 6 patent published. So we have visited the completed 3 foreign assignments. Also, Dr. Anil Kumar Viru is also already involved in national institutes such as the Global Institute of Academic Network, again, where he has led advanced courses on nano hybrid composites and ceramic materials. Uh, he authored two proceedings in two national and international conferences. Further, he has authored 15 book chapters. He is also a member in ISI, New Delhi, IEI, ISTE, and Indian Foundry. So I'm welcoming him to give the talk or expert talk on the topic. So thank you for being here and giving time for us for the session. Okay. Thank you, sir. Please.
Thank you, sir. I should thankful to you and your team that you're working, sir, giving me opportunity to interact with you that national forum. I'm very much thankful to you, sir. And yeah, and respected dads are also given the consent. So it is an institute level program of the both the institute. So not wasting much time. So I would like to go further. Uh, Today, I would like to say that it's our very unique topic where the computer science people, where they are working a lot in the biomedical as well as, where mechanical students, mechanical also can, take the participate and, make further. So my topic is that intelligent computer-based technology in dentistry. So it's uh, how the we can use you can integrate in the area of dentistry by intelligence by artificial intelligence by artificial intelligence ocean, so we can apply any of the tools in it so that it can be come into in a productivity way. So basically this workshop is meant for the development of the faculty development program. So ultimately, the faculties and should make the society's change where the society also expecting. So and further, I would like to say that the French professor Dances has introduced the CAD CAM in the dentistry in 1973, and he was considered as a digital dentistry, uh, where in conventional case, the people are using the conventional mode of techniques where to resolve the issues of the problems of the patients.
Sir, please unmute yourself. You are not audible, sir.
So here, sorry. So here, the patient has to stand still and make the things very clear in the diagram, and make the arrows, making the very complexities things where he has to make the exact problem to be located. And this makes the patient also already they are in problem. Why I am telling that AI assisted, because ultimately what happened as a AI, artificial intelligence based techniques, what we have to do is that we should make the user friendly techniques. You should make the user friendly things to the patients. So we are, we basically focus on the, the doctors will focus on the accuracy, precision, and everything. They will be, making things. But above all, I would like to say that, the patient should get the comfortness, earliest, as already is the pain and is coming to doctor, some sort of anxiety will be there, and where he has to make the all the diagram and everything he has to do, and things are prolonged. So here what happened, intelligent digital analysis, what we will do is that we can take the CBCT scan data over it, CBCT scan data over it, and we will be knowing that the exact location where the dislocation of the tooth has happened, or any flaws which have been identified in the tooth itself, or is there any make of the dislocation of the things, anything, we can make with the CT scan, CBCT data, we can take it, and where we can identify with the proper location, and it will be happen, with a fraction of time that a splash will come, that like taking the picture of it, and we can take it, and we can use for it, for the n number of times we can analyze. So in this way the time consumption will be less. Hardly, within 5 minutes or to 7 minutes, we can complete the assignment of it, and then the doctor can take the next course of it. The traditional way, as you see, that the time consumption already I said that, and also error prone, maybe some sort of, always, as the patient also been standing, and respectively the doctors are also been taking the things, some sort of human error is chances are there. So, and it is, and so, and second thing, one of the important concept I would like to say is that uh, difficulty to store, as storing the data is important. Okay, once in the AI based things are there, where we will be talking about the clouds, where we can save the data, where we can retrieve it back, and we can use for the multiple times as the patient's needs. So with the high inter observation variability can be observed. So this is the where we can make in the the pros in the cons in the pros and cons in the traditional way. So in the modern digital method, the AI assisted software, it is a faster and a precious, and consistently, we can make the analysis with the improvement treatment, and uh, in this analysis, and the transformation in the is will be faster and easier, and it also more precious in the healthcare system. So I would like to say this, one point here, that we should take that what are the main things which we require uh, uh, in the traditional case we'll be seeing, and we will be solving in that only. Whereas in the modern digital technology, please listen, this is very much important, but whereas in the modern digital technology, in the AI assisted, we can see the number of problems we can address in the one CBCT scan data. That is very much important, as uh, in this I would like to say. And next thing I would like to go for the next slide. So here I would like to say that, uh, generally the figure looks so interesting of it. Uh, Here we can check the here I would like to bring the I just give me 1 minute time, not even 1 minute. I'll bring the impressions of it, and I will show physically 1 minute. So I would like to say that in this thing, if you see the two impressions of it, I'd like to say, hope you are understand listening. So these are the impressions in these things where you can see that the if any of the problems which you are having, so they will take the impression of it. They will take the impression of it, and they will make the casting like this. So we can see this thing where you can see the you can see this is the thing, part of the things where you can see the flaws which you are having here, and again it is a flaw is having here. So you can see how makes these things are happening. The things where we can go for the impression. So this type of making this this way of traditional way, if you make it, and it takes a lots of time consumption will be there. So here we can see that the whatever I said that here I showed is a conventional impression on the in the thing, and here stone cast as you said that, and where you can see it, and then what happens, we can go for suppose it takes the time of it and extra oral scanning if it is want to make the things, and with the same thing also we can take we can two types of things we can do. Once we do the casting, we can wear the investment casting, and we can do, and the same thing also if you want the things, you can go and the CBCT, you can send a CBCT scan data of it, and you can measure up for it, and here extra oral scanning where we'll do for it, and we'll go for the manufacturing, and we'll go for the additive manufacturing. So here what happened, the internal in this way, in the second way of AI based things, the scanning, intraoral scanning, where we will do intraoral scanning, then we will design the CAD design we will do, and after that what happened, the digital wax up and articulate and allocution. So what I would like to say is that make the very clear, this CAD design will be making the things, this CAD design will do, and here with the mesh measure software where we can do the Cura software where we can do 3D slices where we can do the soft we can use the different softwares, and we can extrude the things, what the things which are not required, and then we will go for the exactly what we required, we can take forward. So then we will go for the further manufacturing. Here I would like to say that the two way of manufacturing are there, where additive manufacturing is there, subtractive manufacturing is there. So prior going for the additive manufacturing, I would like to say to all of you that subtractive manufacturing means cutting the already one volume of the suppose if it is there here, it's a complete product, it's a solid object. In the subtractive machine, we will cut and we will make as per the requirement. We will remove the excess metal, and we will design. We will be the actual thing. We will portrait it, and we can do. Means ultimately we are taking solid product we are taking, and then we have been cutting off, and then after that, after cutting, we will get the actual requirements already, because I am wasting my excess material. Whereas in the 3D printing, where the additive manufacturing 3D printing, we can go for the layer by layer manufacturing. There is nothing is there. It starts from the nothing, and it will come with the product. This layer after layer after layer, it will be fabricated. So here, what AI takes the role is that AI took the role is that in designing and in manufacturing of this any crowns or, no, or any of the mandala or any of the things where we want to fabricate, this will the AI ML will take a role of it here. How much the precision the data that we can take, and whatever the data that we have been taking, that may be having the error. So we have to minimize the error. That is important. Where the AI can take the room of it, and we can make minimizing the error as much as we can. So here I would like to say that in the aspects of it, in the impression, we can go for the physical modes, and here we can go for the modern dentistry, digital scans where we can do, and the diagnostics where we can do the 2D X-rays we can do, but here we can go for the 3D image and AI, artificial intelligence, and crown fabrication. Suppose, as I said, that if any other tooth which is there, I can put a cap over it, and it's a in the traditional way we can the lab will be produced with different techniques with investment casting. It takes so much of time, whereas in the whereas here we can go for the computer design and computer manufacturing. The same day the crowns can be manufactured. And the other thing is that patient comfort, as I said you that very clearly. I would like to it's a very key takeaway in this workshop in my talk is that the patient comfort is very much important. Ultimately, the healthcare where before 100 years also, before 150 years also, the healthcare system was existed. But it takes so much of time, and as the time increases, the suffering of the patients is more, and the patient will be a trauma where it cannot measure it. It's difficult to measure. So what I would like to say is that the patient's comfort, at a short time, it makes a difference for him to continue his life. So here treatments multiple times he has to visit, whereas it is where we can go for the faster workflow we can do, and precision, the technical department, the technical experts are there. So where the based upon the technical expertise, the things are varied with the person based, because his involvement is more. So suppose if the operator changes, again the new operator comes, but he may not regain the same thing which was the earlier operator has been there. So the technical department has to take care of which one that he has to make the things. And second thing is that high accurate digital planning. So here we can have the high accuracy. We can go with the digital planning, with orientation, with the size, shape, with aesthetics, how it looks and everything. And record keeping is very much important. As I said you that as a computer engineers, you know better about keeping the manual things. No, it's occupies so much of storage, and over a period of time it may not long last. To retain that copy. After 15 years or 20 years we may not get. Whereas in the cloud-based digital systems where we can keep the patient's data safely, securely, and whenever we require, we can retrieve it. That is the key concepts in the AI ML based. As you know much more better than me that cloud-based how we can cloud-based digital systems works to preserve the data. And here I would like to say that AI integration in CAD/CAM. So here I would like to say that as a computer engineers, where we will be taking the your help that much more, that where we can basically the Python languages, C++, Java, Fortran, earlier was Fortran, so much of languages are there. they used to execute the things, make the things, faster. But what I would like to say is that as we, the mechanical engineers, manufacturing people, where we will do is that, and the AI that what the CSC department people have been working, when we integrate it with CAD CAM, computer design and computer manufacturing, where we can make the things very faster, and where we can go as much as population as we can. So here I would like to say that there are the four sets. I would like to say that clinical decision making and computer design, computer machining, or we can say that manufacturing and CAD CAM materials. So these are the four sets. I would like to say that the clinical decision making, the virtual smile, and simulation, where we can see that how the things are there, and prediction and restoration of the physical durability is one of the key concepts in the thing, and the prediction of and of restoration of the bonded durability. So this is one of the key important point where we can see the prediction. So I will share my one of the case study for my scholar work. Also, I would like to say the time permits. So and computer design, where the web-based designs, where we can do the web-based design, and we can go for the automated biometric design we can do, and AI suggested to restore the design, and integration of facial symmetric of the precisions related factors. So the personalities, which it's varies from the different to different persons. The integration of the facial and the personality related factors are to be taken in the design, and integration of the previous successes restoration. So previous data, how the previous things are happening and how the present things are happening, that has to be addressed in the CAD design. So, and one of the important thing is that the scanners, initiative scanners with the automated finish lines detection and image segregation. So once the image is there, it is a pixel form. It has been there. The magnification, the resolutions varies once, making the taking one place to another place, as the it will degrade. The here what happened, the image segregation is important while scanning, and chair side and lab based initiative designs, where we have to intuitive prone. It's the innovative way of mode we can design. So computer aided machining, the repetitive machining tasks are to be automated. Where we can make the thing one. If you make one program for it, and we can execute. So here, what I would like to say is that what the CAD has been made, design has been made. So you can write the programming of it, how much depth it has to go, how much width it has to go, and how much circumference you can has to go. It all things we can take the tangible data, and you can run the program. And once if you run the program and once it execute, then you can integrate the AML to the system. Automated system, where we can fabricate with minimum errors. So the here one of the important thing also, we can see that the uh, biomaterials in the CAD CAM materials also there. We can set the material developments also we can do, because I'm telling that the as the time span increases, the materials also changes. It's keep on we can make this. So as a in a AML, one of the important thing is that once you write the program to the once you write the programming to one of the aspects of it,
Sorry,
and
sir.
you have
Interruption, sir. Your slide is not updating, sir.
no
Kindly
no
check
no
it.
okay.
Not updating
uh
Zoom meeting.
Now it's there.
Uh, no, sir.
AI integration in dentistry you have seen, na?
So which page number, sir? Slide?
Page number 4.
No, sir. It's not updating. It's showing the first slide. Yeah, sir, it's updated. Now it's updated.
So now, so yeah, here we can see that composite strengths we can see of it, and automated material properties we can see, and with the evaluation and the prediction. So here one of the important thing what I would like to say is that the material perspectives, as the CSC people, as a computer science people, what we will do is that once you design the any of the programming, and you will be taking all the material perspective, all the material properties you will be taking, and you will be executing. So here what I would like to say is that very clearly that once you write any of the programming, once you write the programming, and over a period of time, the material property changes. Again, you need not to go for the repetitive writing of the programming, and you should have the library, uh, uh, and we can retrieve. We can if I want to take the we can update the library data based upon the we can call the material, and we can run the programming. Suppose if the patient having the economy patient having, suppose if want to go with the simple material, where you can run the programming by taking the with a simple material like PLA material. Like material PLA material is a material we can execute, and we can execute. Suppose some of the wealthy people comes, suppose with the peak material that we want to make, then we can call from the library the peak material required, then we can execute. What I would like to say in this platform is that in this thing, sir, whenever we call the material properties, that has to come and that has to execute, because we can what I would like to and say that once you write a programming that we can make use of it for multiple operations of the same domain. I'm telling them. So in that way, what happens, so that the doctors may not having that much of time, again calling the computer engineers and make the changes and everything. You should make the things, make the things in a broad sense, so that we can call it and we can execute the things. So here data mining, much we collect the data, and machine learning and virtual simulation, and neural networks, and prediction models, and knowledge-based systems, and augmented reality. Means virtual reality, we can go for it, and fuzzy logics and deep learning. So these are the one of the AI tools where we can use in the dentistry. So I would like to repeat once again the data mining and the machine learning and virtual simulation. Before going for the actual way of for fabrication, we can go for the virtual simulation, and with the neural networks, there's a back propagation technique also, and a feed forward technique also there, and we can also the ANN, artificial neural networks, we can use in the AI, and predictive models. As I said that once we have the data, with so much of let's say 1 lakh patient data you are having, so we can make the predictive and we can take the data and we can execute it, and we can do. So here I would like to say clearly one point, taking the gender and age, 2 factors, and once we get the data of one patient with the problem and everything, and what the solution that it has happened. So if you keep the data like that, so much of data you have been incorporated. If suppose same type of patients are coming with same age and the same gender, people are coming, so we can call from the data and we can predict what exactly we can do, because already one patient of this case already has given the solution. So again, need not to go for the if experienced doctors are there, we given the value of it, and if junior doctors also there, they can call it, and we can go for the necessary process of the fabrication, and go for the clinical things. So there's a knowledge-based systems where where we can go for the anatomy part, where we can go for it, and what the medicines, that what the treatment way of giving the medicines based upon the treatment, what medicines they have given. The knowledge-based systems also can be stored of it, and we can go for the augmented reality and fuzzy logics where we can make the rules for it. Then we can go for the deep learning. So this is the one of the important aspects what I would like to say in this today's presentation. And I am going for the fifth slide. Hope you got the fifth slide also. You got fifth slide, you got now? Hello? You got the fifth slide, right? Yeah. Hello? Hello?
Yes, sir.
Yeah. So because I need your attention, please. So here I'd like to say that here data collection, as I said that AML and machine learning workflow, that data collection is one of the precious things, and data radiographs where we can go for it, and clinical records where we can go for it, and internal images where we can go for the internal images of it, and data pre-processing, and the noise removal. The noise removal means the what are the which are the things which are excessively which are there, not related to our problems. Means noise means generally it's a noise. The term that we have used is not the noise, the voice that which is unpleasant to hear like that, but it's a noise which is having a not required. May not be have that much of essential for our things. So we can go for it as a noise removal. Means what are the excess things which are there, we can go for the noise removal. And then we can go for the image enhancement. And we can go for the enhancement of the image with clarity and everything. And labeling and annotation is important. So here in the image where we can go for the annotation, the labeling part we can go. And a feature extraction, suppose if you want to tooth boundaries, we can go for it. And lesion detection, we can go for it. What are the things which are having the flaws where we can go for it here. Here we got in the second things, we got not that much of clarity, but we got here the detection and also structure abnormalities are there. Suppose it is there, the dental things which are there, we can see here is a flaw which is there in the teeth arrangement, we can see. And clean and decision support. What I would like to say is that AI assisted diagnostics and improves the treatment planning and better patient's outcome. So very clearly, I would like to say that the decision support, as I said in the earlier thing, that the knowledge-based system which were there, that will make us the clinical decision support. How much knowledge, how much input data that you are giving, and how much with the input data of the particular patients you are giving, and you are been segregating and putting in the library. Then on the basis of the decision support will be much more precious when you have the ample of data. Then you can call it and you can make the you can get the assistance, and the restoration and reconnected can be possible for it. And prediction and classification where we can see that decision detection and treatment recommendations where we can go for it. And modeling also we can go for the modeling and machine learning and decisions support this modeling. We can go for the pattern learning where we can go. Key takeaways is that the machine learning and digital learning where we can go for it. High quality data and intelligent analysis leads to the accurate diagnosis and the better treatment outcomes. As I said that now very clearly that how much data that we have been having, that much of precious thing that we'll get it. So this one is a thumb rule. The AML. And I went for the sixth slide. Hope you got digital image and data acquisition. That CBCT scan data, as I was repeatedly telling to you that for the CBCT data is there here. The cone beam computed tomography. It's a tomography is an image, the image where we can see that the CBCT scan data and 3D visualization of the oral structure and accurate implant planning. And we can go for the scanner. That is the inside where we can go for intraoral scanners, where we can go for intraoral scanners, where we can go for the, we can send the, a device of it, and we can bite. Once you bite it, digital impressions where we can see for it, and we can go for the improved patient's comfort, and where it comfort and how the pain started. Then we can take for the scanner, and digital radiography. We can faster image acquisition, where we can use reduce radiation exposure. So here we will not go for the CT scan data, but tomography data is generally compared to the CT scan data. The CBCT scan data is less influential, less harmful to the patients. So that is also a very much important thing when we go for the ethical things. So, and 3D imaging, as I said you that very clearly, that the 3D imaging is a better anatomical understanding and improved surgical precision, where we can go for it. And here that improved, it has been, once we go for it, the improved solutions where we can go for the restoration has happened. So that the key visuals are CBC scan image, and intraoral scanner, and digital dental model, where we can see the key visuals, where we can see. So here I would like to say that key takeaways is that AI performance depends upon heavily on the image quality and data set accuracy. So for the basically for the AML, one of the important thing is that how the image quality is there. Very much important. Once the image quality is being compromised, then if you go for further process, further in the next course of action, if you go for the fabrication of it, the actual problem which is there, and it will create a double problem. So the image quality should not be compromised before going for the fabrication. You have to identify that how much error that the machine has been happening. The trail you can go for it, and then you can go for it, and then based upon it, the error correction factor should be implemented. So more error corrections are being not advisable. So that is why it has to be negligible. It has to be very low, and so that the patient's comfort can take a course of action. So AI-based diagnosis, this is where you can see for it. Dental caries detection, automated cavity identification, early storage detection, where we can see for it, and in the predominant disease analysis, like bone loss assessment and gum disease monitoring, where we can see the oral cancer screening. So the less classification, early detection improves the survival rate, and the root fracture detection. AI-assisted radiographic,
Excuse me, sir. The page is not updated, sir.
oh,
The
the
slide.
page is slide is 7, na?
Sir, it's not updating, sir. Kindly check once, sir.
Now it is updated.
Yes, sir. Fine, sir.
Now it's updated. Slide 8 you are doing.
It's the slide 8, yes, sir. AI-based disease, yes, sir.
Slide number 7 we can see here.
It's a slide
The
8, sir.
title.
AI-based diagnosis.
Oh, yes, sir. Perfect.
Okay,
AI-based disease diagnosis. Thank you. So here I would like to say that as you know that the cancer, I'd like to say that very clearly. I would like to say that there is a, if we want early detection is not there, if it is early detection is not happening, like in the case of cancer. So then if the time span increase, if the time span is passed, then it is very difficult to get to come back. So this identification of several periodic aspects using the things you can just compromise the margin if you are taking, and carriers you can go for it, and bone level 4.3 where you can go for it, and bone level 3.6 we're varying for it. The images hope you are seeing the sizes 2.1, 1.8, 2.8, bone level 3.6. So these levels are being varied, from tooth over to the tooth. And another further, if you go for the calcus, the calcus which are there, or the color changes the tooth, and it will looks like the things, then it will create so much of fun. And bone loss for 2 to 4 mm from the CEG. So I'd like to say that how as the calcium increases, the bone loss will be taking place. So while biting, suppose if I bite the things, then the they will bite the things, and the losses will be the law. You think that suppose if I make the do like this, and then with the crushing of the tooth each, then the loss of tooth has happened. So even the 2 to 3 mm, 2 to 4 mm, it's a huge loss, because the whole thing of the tooth which have been there, now it will be around 5 centimeters, like that. Not even, sorry, is around 2 centimeters, one cent. Sometimes if you go further, it is the decreasing the size will be there. If you go further, if it is go for it, so it may be of 5 to 7 centimeters if it is there. If it is there, so then what happened? Then you have to the loss of MMs also huge loss. So this is important where we have to address. And deep learning and computer vision. I am going for the slide 8 now. The deep learning and computer vision where we can see for it. And the conventional neural networks where we can go for the X-ray interpretation, and tooth segmentation, and image segmentation, and object recognition are there. The benefits, what are the benefits which are there is that the high diagnostic accuracy will be there, and reduce clinical workload. Basically, what happened, will make the clinicians to workload will be less. Once the doctor workload be less, so he can have a more, he can put more attention of the patient. Once he keep the more attention of the patient get the right treatment. So that is why we are AI-based assistants we are giving to the clinicians, and especially in our area, the dentists. Once you are reducing the clinical load, the clinician workload, then he will work efficiently, and his outcomes will be much more, fruitful in the patient perspective. So still there is a limitations. The require large database sets, where, and also to preserve the data sets is also one of the important thing where we have to see. And computational intensive, where we can go for the computational intensives, where we can go for it. And input image and conventional, which is there here, and cooling and flattering and flattered things, and again we will go for the y1, y2, y3. So there is a feature extraction where we can go for the feature extraction, that is a conventional cooling and the flattering, where the flattered things where you can go for the image to the image analysis, where you can go for the y1, y2, y3, like that. So ultimately what happens here, uh, the the data sets that we are having should be organized in a systematic way, and can be called at any time, and can respond as per the problem. So here I would like to say that the slide number now orthodontics and digital smile design. So here I would like to say that very clearly, as I said, that data collection. So the CBCT scan data and the intraoral scanners which are there here, where we can go for the data and we can make the things different. And the facial and the intraoral photographs, where we can go for the photographs of it and we can make the things. And here the artificial intelligence in orthodontics is that data collection of the experts of automation, and here AI training and AI output and experts refinement and AI training. So it's a cyclic process. The training is the cyclic process, or has to learn from the lifelong learning. And AI tools is that what are the things that we can do that, as I said, CBCT segmentation and tooth segmentation, landmark identification, dental monitoring, the facial attractiveness evaluation. So these are the AI tools which we are having, that CBCT segmentation is one of the key and initially starting things. So recently we also visited RIMS and we also taken the CBCT scan data and we can execute it. So CAD CAM in the dentistry is that very clearly. I would like to say that data acquisition is there, where we can take the data, internal scaling, CBCT image, and digital design, and where we can go for the crown fabrication, or we can go for the using the appliances using the CAD software, where we can see for it, and STL file. STL is nothing but stereolithographic file exported and prepared for the manufacturing slicing. So here also say that the object is fabricated using 3D printing as subject to mailing. So here I would like to say that the product that we have been fabricated here. Here, if you see for it, this is the 3D printed products that we are being fabricated. So this fabrication of the mold, and here you can see the volume of it is different. So here the same thing, you are going for the fabrication of the tooth structure, and then post processing can go for the, and what are the things which are to be corrected and everything. Then you can go for the final product. One is digital workflow is there and physical workflow is there. Physical workflow starts from the 3D printing. So there's two things are there. One of the things are there. Basically, the as a computer engineers, the digital workflow is there once you are writing the programming part, and where we can go for the virtual, we can go for the virtual reality, or we can go for the virtual, analysis or design and everything, where you can go for it. And secondarily, what happened, the physical workflow, what happened, once the 3D printing started, so then execution part, once it started the execution, you should send the data, what are the programming that you have been executed, that has to be addressed in the, it has to be incorporated and that are executed in the physical workflow also. So both cases, in two cases, the AML is been used. Many people has a perception that AML is only for the designing part or analysis part, and we are not it's not our cup of tea to make the fabrication. No. So from the starting point of this analysis and selection of the image and everything onwards, to the problem to the solution, you are been, the AI can assist. This is one of the important key takeaway for you to people. So the fabrication part, how the AI makes that, what are the signals that you are giving, that has to be, will send it, and that has to be function. The functioning part also taken care by the AML. And here the robotic smart dentistry, people know that with the knee replacement and everything has been in the orthopedic things, where you can people are thinking that in orthopedic things, the people are going for the robotic things of operation like that. It's quite interesting that even the dentistry also going for the robotics. So here the programming part is there. Once you take the data for it, but drilling, we'll go for the drilling operation. Suppose if I want to go for the, suppose if I want to, this is a thing where I want to go for it. Suppose if I want to make the drilling. So what happened? The doctor, the dentist will make with the hole with the drill which is having. Make the drill hole it and will fabricate it and will fabricate and make the drill. Whereas the and he will see that he will see he can access, it is not required that much of access to go, he may go for access, or he feel that he is panic that he cannot go, but it has to be go, it has to be sent some of the depth. So then also the clarity may not be having for the doctor how much depth and how much width that he has to go. But whereas in this case, once you take the digital image and make that how much depth the flaws are there, we can write a kind of programming, and the whole fabrication will be made as per the written programming. So very clearly I would like to say that which have a less human interaction and less error might be there. So the workflow is that CBCT scan data is there, and you can go for the treatment planning of simulation where you can go. A surgical guide, we have to see that very clearly that we cannot go abruptly because we are dealing with the humans. The much more ethical things also we have to take into consideration, and final restoration and follow-up also very much required for it. Reduce the surgical error and minimum invasion and faster recovery time and improved patient outcome. So this teledentistry, which is there here, that online consultation also we can do, that the remote diagnosis also we can go now. Even the rural sectors are there. We're going for the telemedicine and with the AI integration. And follow-up also very much important. Generally, what happened once we get the things done very clear, once we have been comfort after taking the taking the treatment, we got something better, so we will not go for the follow-up. And we feel that okay, that much of long distance I have to go and I have to take appointment, I have to wait, and my time is to be there. Not, but teledentistry, where you can go for it is that whatever beautiness is that the telemedicine, teledentistry, one of the teledentistry, the useful things are there. The follow-up can be done, as per the scheduled time which you are having, and we can execute the things in the telemedicine. So once the follow-up is there, when the recovery rate is fast, and things are can be checked properly in the short span of interval. So in the telemedicine, so cloud-based healthcare, as I said here, that the data collection should be the cloud-based, and it should be patient data secure storage, and it should be easy access, and it can fall anytime. So this is one of the important thing. And AI chatbots, generally what happens, and with the computer also we can go for the chat box for the problem which you're having, then they can say once you give the clear thing idea. What are the clinical challenges which you're having? Slide number 13, I'm saying now, the clinical challenges or and ethical issues. One of the important thing is that limited data sets are there, and image quality variation is one of the technical. Very clearly, I like to say that yeah, image quality to be there, and you also go for the modern generation issue, and ethical concerns, patients' data privacy. They should not never we should disclose the name and region where they have been there like that. So there's also ethical things where you have to see that the AI is biased based upon the person which you are having.
Sir,
Accordingly.
sorry for interrupting, sir. Sir, your slide is not moving, but
What is the slide number?
what, sir? Your slide
What
is
is slide
not
number?
moving.
What is the slide number?
AI-based disease diagnosis, sir.
Now you
Sir,
got?
no, sir. Sir, also we have time, not more time, sir. So limited
Yeah,
time.
time. I'll complete. So what
Okay.
are the things that you are having now? Slide number?
Slide number
Slide
8,
number
sir.
8, sir.
Huh?
Slide number 8, sir.
Uh, challenges.
Yes, sir. And people issue.
Can you write the title of slide? Can you read this?
Challenges and ethical issues, sir.
Yeah, thank you. So here the challenges are there. Here we can go for it. The limited data sets are there where we can go for it, and image quality variations are important, and model generations are there. So what are the ethical concerns? The data privacy is very much important, and by AI bias means giving the data, wrong data if you interpret, and it will keep on being there. So that should not be there, and accountability should be there very clearly, because we are dealing with the humans. So the ethical concerns are important. We have to go for the proper ethicals, and clinical challenges are there, and accepted by the practitioners are very difficult, because the doctors' mindset are like this. So for them to make the to go for the new adaptability is difficult, and the high implementation at initial stages, the cost is more. The regulatory approval is required. So these are the things where we can go for the better diagnosis, and you can go for the improved patient experience. We can go for it, higher efficiency and safer and sustainable responsible care. We can go for it, and future trends in research opportunities where you can go for it is that. Hope you got the slide number 14. What is the, can you read the title of the slide?
Challenges, sir. Challenges and ethical issues.
Huh?
Challenges and ethical issues, sir.
Future trends
Now?
and yeah, future trends and research opportunities.
Yeah, thank you. So it's a generative AI is there, and digital twins, generative AI, automated report generation is possible, and digital twins, to virtual things we can model it, and preview simulations where we can do, and augmented reality and virtual reality, AR, VR, augmented reality and virtual reality, we can go for it, surgical training where we can go for it, and biomaterials which are there very much important. As I said, that library, calling the library, and going for the larger scope for the incorporate the new materials, new developments are coming, new materials are there. So, and research opportunities, AI assistance, biomechanics, and FEM analysis, containment analysis in implants, and pre-tube failures are there. So these are the important things where you can take for it. And here I would like to say conclusions. Dentistry is rapidly evolving conventional practice, and in the healthcare system, and AI, ML, artificial intelligence, and machine learning improves the. Hope you got the conclusion slide.
No, sir. Yeah, slide. Yes, sir.
Technologies such as CAD/CAM technologies, 3D printing, robotics, and computer vision and transformations are there. You can go for it. And telemedicine, as I said, that it improves accessibility in the remote clinic health also. It's also, despite advancements, data privacy and ethical concerns also important. And AI should accept the support tool and enhance, not to replace the professional clinical things. And thank you so much. I would like to say one small thing. I don't know, just one thing I would like to say. If just give me 1 minute time, I'd like to say to you, I'd like to share my try to so here is our practical things that the development of patient specific 3D printed hip fabrication we did for the surgery planning. We have fabricated the hip, 3D printed hip we have fabricated in our lab, and accordingly the doctors has given that the surgery, how the surgery has to take place, and make the things like this. And here the surgery took place. Here they kept the implants over it. Nicely they put the implants. How they are organized. So the surgery times has been the surgery time has been minimized half an hour. Earlier it was 3 hours and it was come to the 2.5 hours. So once the surgery time is less, the infection rate also will be less, and so the patients will have faster recovery and the safe the patients. So these are our practical cases where we have made our study. So I'm thankful to sir that giving opportunities for the thing. So
Thank you, sir, for your wonderful talk. As Ujjwal sir is currently busy now, so I am conveying my gratitude on his behalf as well.
So I'm thankful to the Ujjwal sir and the other coordinator from the college, Jyothi College, and especially to my director and your principal and chairpersons who are there. Thank you so much for giving the opportunity in this platform. And and also my for participants, I would like to say one thing that please think that if we need not to change much, but overnight we cannot change. But one thing is that whatever the small efforts that you are been keeping, and that will change that will change some sort of societal impact will be there. If small changes are there, for larger people sections it is implemented, so that is much more happiness in the healthcare system. Yeah, that's what we need not to do a rocket science. It's small science, small contribution makes much more difference. Thank you so much.
Thank you once again, sir. I truly appreciate your guidance and inspiring words. So
Yeah.
we can end
Okay,
this
may I
meeting.
leave then?
Yes, sir.
May I leave? May I leave now?
Yes, sir.
Our participants are requested to fill the feedback form.